There is. Let me turn this off. Good morning. Can everyone hear me? How's everyone doing? Excellent. I like it. That's good. That's not bad. You guys must have had your caffeine already. We're going to start in just a minute here. Just want to get everyone's attention. And so thank you for coming on a Sunday morning and skipping church. Appreciate it. This is the Church of Mars. Is the Reverend here, the gentleman who gave the speech? Yes, Reverend, I want to congratulate you. You gave the most intellectual presentation of the entire conference, and that came from a Reverend. I was just outstanding.
Excellent. Well, I'm so excited to see everybody's faces again on a Sunday. I know everybody's tired. I'm sure you've got, travel plans to get home, missing church this morning, but we appreciate you being here with us. Want to go ahead and introduce Kai Stotz, who is a veteran developer of platforms for research and science education. He was co-founder and CEO of the world-renowned Yellow Dog Linux operating system for 10 years. The YDL platform was used extensively for the Department of Energy, NASA, and university research across a spectrum of sciences. At Arizona State University, Kai led the development of CMOC, a research-grade computer simulation and educational interface hosted by National Geographic that enables citizen scientists to explore the complexities of a human habitat on Mars. Now, Kai and his team have constructed SAM, a high-fidelity, hermetically sealed Mars habitat analog with greenhouse, living quarters, airlock, pressure suits, and half-acre Mars yard located in the iconic University of Arizona Biosphere 2.
Thank you for the introduction. Appreciate it. That's my whole talk. Thank you. We're done. Straight to questions. Yes, thank you. It's like some of those films where you see the trailer and you realize you really don't have to see the film. So last night at 1:30 a.m. as I was working on my slides, because I don't procrastinate, I realized that I had two titles. This is the official title, and the second title is Why I Will Never Again Remodel Another House. So the SAM effort, as I will show you, and for those of you who were here, how many of you were here last year and saw my presentation last year? Excellent. This is a continuation. It picks up where the other one left off. You remember the last year I described the first year and a half of construction of SAM. We had a video and a lot of slides of welding and cutting and grinding and fabricating. And I'm not going to show a lot of that this time. We're just going to skip to the end where we have the thing up and running and really give you a tour of SAM. So this is the 8 biospherians who were sealed inside of the Biosphere 2 experiment from 1991 to 93. And if I had a longer presentation format, I would definitely go into the history and the depth and the incredible science that came out of that project, but we're going to keep moving. Before they built the Biosphere 2, they built the test module. This is on the same campus. It's about 200, 300 meters away. And this test module at the time of its construction in 1986 and 87 was the world's largest sealed experiment in human and plant ecology or symbiotic relationships. So it was a phenomenal breakthrough at that time. And each of the biospherians took turns living inside from a couple of days to the record was 3 weeks by Linda Lay, who is now lives in Oracle, Arizona, just outside or just past the Biosphere 2. So this is what we started with. And if you remember the presentation last year, I showed you pictures of about 6 inches of feces and dead animals and cactus. And it was quite the effort to undo 25 years of lack of use and abandonment. And we got the thing up and running again. And then we added on and extended it. So this is an artist rendering and an overview. In the bottom left-hand corner, we have the original test module. And then we added on a 20-foot shipping container. And that is our engineering bay, and then a 40-foot shipping container, which is the crew quarters, kitchen, and toilet and sleeping facilities, and a fully functional airlock that we stole from the basement of Biosphere 2, was used by the original biospherians. When I say steal, that's not quite accurate. The deputy director does give me permission, but he says, just go do it, just get it done. And this is an interior view of part of what will be our 3,000 square foot indoor Mars yard with fully synthetic sculpted Martian crater walls. And we're actually in construction of that now and have been for the entirety of the summer. So these are the actual photographs of the facility. And just taken this spring, just before our first team entered. Again, the test module on the left, the engineering bay in the middle, the crew quarters on the right, which you're seeing just the end of the 40-foot shipping container. And this is looking into the original test module again, which we fully refurbished in the spring of 2021. There's a wonderful story, if we have time at the end, about the flight number, the N1987B. That's actually registered with the FAA. I'll tell you the story about how we obtained that. It's probably not going to fly. This is the outside of the lung. The lung is a variable volume pressure regulation module, a wonderful invention, not invented by the biospherians, but as far as I know, the first implementation at that scale. So we have a fully automated analog, meaning not digital, not mechanical, gravity-fed pressure regulation system on the test module, in the test module, and then the extension of our entire sealed facility. And this is the other end of the crew quarters with an emergency exit. And these are just two views of what will be the Mars yard and our workshop. So all of our fabrication, almost all of our fabrication was done on site, almost entirely with these 10 fingers and those of my staff, who I don't know if they're here yet, but we'll introduce them later. Some of them? Okay, excellent. And so we've had 2.5 years of volunteer and paid staff working on this project. I'll introduce those folks later. So I just want to go through the core components of SAM in its current state. So we have the greenhouse, now currently called a controlled environment. We have a crew quarters with sleeping pods. I'll explain maybe a little bit later. Common area toilet and shower, a kitchen with fridge, stove, modern appliances, and a wonderful biomass or inedible biomass to protein converter, which worked exceptionally well. A workshop with a 3D printer, sewing machine, electronics, repair bench, tools, and computers. and of course the lung as the automated pressure regulation system. We have a fully functional airlock. It actually works. It pressurizes, depressurizes in about 30 to 45 seconds. We are maintaining just 1/10 of a PSI over ambient, but it's enough to apply about 150 pounds of pressure on the doors and almost 200 pounds of pressure on each one of the windows. It's enough that your ears, for some people are sensitive, your ears do pop, and you definitely know that you're inside of a pressure regulated facility, which really changes the psychology of being inside of SAM. We also have a life support compartmental control, meaning we have 4 mini split heat pumps. So we both have heating and cooling to maintain a constant temperature all year round. We also control relative humidity and capture all the condensate for drinking. So all of the air you're breathing out, the water that is produced by plant respiration or transpiration is also captured and recycled 100%. And of course, the outdoor, we have an indoor and outdoor Mars yard. The indoor Mars yard is what we're building this year. And then that leads into the outdoor Mars yard, which will be sculptable on an as-need basis. So if a team comes in for an extended period of time, they can ask that they have certain set of craters over that 1/4 acre, and we'll be able to sculpt those using bobcats and bulldozers and such. Yes.
Check that
Okay.
sharing for Zoom.
Okay,
Sorry about that.
that's okay. Oh, are we getting some feedback?
It stopped for some reason.
Okay. I'm gonna minimize this real quick.
We can do that.
Yep.
Hide.
There we go. Cool. Oh, back one. Okay, there we go. We have full use of pressure suits. How many of you saw one of the 2 or both of the pressure suit demos? Okay, excellent, good. Those were designed, the versions we have by Dr. Cameron Smith. Cameron, are you here? Excellent. Here is Dr. Cameron Smith. And that particular version, of course, was collaboratively designed by Dr. Cameron and Dr. K. And outstanding. So we have 2 earlier versions of that without the neck dam and the CO2 in the bottom. And all of our EVAs are conducted with fully operating pressure suits. And I've had the honor of knowing Cameron now for 10 or 12 years. We met at the Mars Society conference in somewhere in California, if I remember right, or it was in Colorado, I think. Yeah, a number of years ago. So we also have integrated CMOC, which is, well, there's 2 versions of CMOC. One is it's a Mars habitat simulator that I actually started here at Arizona State University in 2016 in the School of Earth and Space Exploration Interplanetary Initiative. We went on to get a substantial funding, and we're now funded by National Geographic Society to continue that. We're in our 7th year of development of that platform. We just open sourced it this summer, so it's available for download. It's a Python and JavaScript environment, and I'll speak a little bit more about that later. We have a live version of that works with a live sensor array, and I'll show you some of the data that came out of that sensor array as our life support monitoring system. And we will be this fall and into 2024 working on mission control. We have a 1,200 square foot building that we just haven't had time to get back to, but we've had it available to us on the Biosphere campus for 2 years. It's about a 5-minute walk away from SAM, visually removed, but in that mission control center will be a den, a library, a place for people to stay the night, a fully equipped kitchen, a workshop, a conference center, and of course a bathroom facility. And all it's there, it'll go pretty quick. It's an existing building, not nearly as hard as building SAM. So I'm going to give you just a quick visual tour of the facility. This is entering the airlock from the outside, and then the second image on the right-hand side looking back out the airlock, and you'll see our spacesuits hanging on the racks, our pressure suits on the racks. We've removed the outer garment simply so that we could more easily get to the constraints, or the pressure suit underneath. And Cameron's going to be working with us to do a special version of the outer garments that'll be more applicable for what we do in our Mars yard. And this is a view from the inside with the airlock door, the second door closed. And again, doesn't sound like a lot of pressure, but it's a significant amount and enough to really give you that sense of being in a pressurized vessel and using a fully functional airlock. We do use the airlock space during the missions. This was not my original idea, but as we know, teams find ways of using things. They end up using the airlock as their changing room, their personal garment room, and we actually hung a curtain across it, so we leave the interior door open, and that becomes their private space because there's not a lot of space in the habitat. This is the crew quarters. which has a kitchen, which is closest to us, and then there's sleeping quarters on the far end. And I used the word maybe in the sleeping quarters part, or sleeping pods. Our original goal for those first two missions was to have fully functional stacked sleeping pods with individual private space. And we'll probably still build those. But what we found is that the crew actually liked picking up their foam pads, which are basically lightweight futons, and sleeping in different places. Some of them, some nights they want to sleep in the greenhouse. Some nights they want to sleep in the lung, or even one person slept in the engineering bay under the 3D printer because it was running all night and she wanted to check it on a regular basis. And so it changes the dynamics, and maybe we need the private space, but maybe we also need to give the crew that flexibility to sleep where they feel that night. Or if somebody's snoring, they want to go sleep somewhere else, which is a real issue. So just some few views of the kitchen. We really had fun putting this together and trying to make it feel much like home as possible. However, it is an all vegetarian diet, all freeze-dried or dehydrated or naturally dry foods. And we were impressed, especially with the second team, at what they came up with for their cuisine. Absolutely extraordinary. And I'll share a little bit more of that later as well. So we have a Instapot, we have a rice cooker, we have a bread maker, we have a convection microwave that does both microwave and hot air. We also have, there's the bread. The first team, I think, made 7 loaves of bread in 6 days. I think they lived on bread alone. And on the right-hand side, I was going to bring a sample, and I forgot to bring it, but I'm really proud of what we accomplished with this. This is a standard off-the-shelf food dehydrator on the left-hand side with silicone trays. And on the right-hand side is a NutriBullet. NutriBullets are those nice little high-power grinding things for making fruit smoothies. So the first team, both teams, all of their food scraps from their plates, from their cooking, is scraped with a spatula onto the trays of the dehydrator. And in the middle or towards the end of their mission, they dehydrate their food, which takes about 8 to 10 hours. It just falls right off the trays into the NutriBullet. They grind it up into a powder. It has no odor. It's completely stable because it's dehydrated. And then we feed it to mycelia, the root structures of mushrooms. And so we inoculate the mycelia we inoculated the mycelia on day 2 or day 3. So the mycelia is now starting to grow. It's activated. We pour this essentially dried food and a little bit of protein into there. And the second team, a week later, was eating mushrooms and sauteing mushrooms made from the food waste of the first team, 100% recycle. There's no loss, 0 loss. And if we have secondary and tertiary strains or species of mushrooms, we can continue that process for mushrooms, eating mushrooms, including any paper waste, anything else. So we're really proud of that. That's our first closed loop. We're now working to close the air loop and the water loop, and eventually the human waste loop, which is not hard, but the county, as you can imagine, is going to throw a fit when we say that we're drinking our urine and recycling our feces. So we'll wait on that one. Yeah, don't tell them. That's right. Where did it go? We don't know. We don't know. So we have just 60 gallons of water, 55 gallons of water for 6 people, or sorry, for 4 people for 6 days. Very little water, and yet none of the teams consumed all their water. The first team used only 40 gallons. The second team, I think, used 45, and I think they splurged on their last day and used 10 gallons on their last day because they could. So think about how many of us take 10, 15, 20 gallon showers. These guys made it 6 days, 4 people on 55 gallons of water. And so we built our own water manifold. This is just an RV pump that we got off Amazon. I think it was a $120 pump. Works beautifully. It automatically pumps when it senses a low pressure or pressure drop on its outside. And we have 3 different outlets for the water. This is our bathroom. And again, the water is running through PEX lines through the entire facility with everything's a manual shutoff valve in case there's a leak, in case you want to change the way in which the water's flowing. We give the crew that ability to manage their water flow. The toilet in particular is very interesting. We always talk about toilets when we're talking about going to space. Turns out that in the course of using this toilet, this is an RV toilet. It's a ceramic toilet with a ball valve at the bottom, which also regulates pressure when you have just a little bit of water in it, and also with a Teflon seal. So it's like being on an airplane. When you flush, there's a little bit of a whooshing sound, but not as bad. And it turns out that we have 2 inlets of water. We have the regular inlet of water that would allow you to fill the bowl. We also have water going to a bidet that we installed on top of it. None of the teams had to use the inlet of water at all. They only use the bidet, and they use their secondary water from washing their dishes to flush the toilet. So all the dishwater, which eventually will be recycled to drinking once we're getting better at removing the grease and the oils, So at least that water had 2 uses as compared to just 1. So again, very pleased it's not a complete water loop, a closed loop, but we got halfway there. And I've asked, why can't we do this in our homes? Well, the reason is that our waste material is doing a straight drop into a tank. And in the commercial, or not commercial, in the residential and commercial systems for which we remove our toilet water, you have to have a large volume of water to flush it, miles and miles downstream. So we can't, unfortunately, you can't use something this low water. We have to go to composting toilets, which a lot of our municipalities are not really in favor of at this time. Again, this is the way in which we capture the water. The bucket on the left is for the sink, which is then used to flush the toilet. The bucket on the right is actually capturing the condensate from one of the mini split air conditioners. We have a fully ADA approved fire detection system. It's a $20,000 computer system. It's really, really loud. I think ridiculously loud. So you almost have to learn hand signals because you can't possibly hear anyone talk if it goes off, but that's what they required. And so it was wired by my team, by Matthias, working with the fire marshal from the U of A. So we're really proud of that in the sense that we did meet their marks, and we have a fully redundant computer system that manages and monitors that fire alarm. This is our engineering bay. On the left-hand side is the fire detection and alarm system. And this is before the first team came in. So there's now a 3D printer there as well. But again, we try to give people some really nice workspaces, good lighting, plenty of power. We have outlets everywhere. This is the interface for CMOC. Typically, you see on the right-hand side some sensors. There's a oxygen and a carbon dioxide temperature and relative humidity sensor, which is the primary sensors. And we have a whole suite of sensors that we gave the teams, all from the company Vernier. We have about 12 or 15 different sensors and portable data collection devices they can use throughout their mission. That's made available to all the team members. Typically, this is its own standalone talk. CMOC is it's a software interface. It's a research grade computer model of a Martian habitat or sealed environment, and it's available to you for free through the National Geographic website to use, or you can download it if you're a developer, or if you want to be able to tinker with the back end a little bit, develop your own agents and such. So this is based on 30 years of NASA data, and it's really quite extraordinary. It demonstrates in a fast forward fashion, 1 hour equals 1 second. It demonstrates the transition from physiochemical to bioregenerative life support, or whatever other scenario you want to set up. So you choose the number of astronauts, you choose the size of your habitat, your greenhouse. You can choose up to 22 food cultivars, how many solar panels, batteries, how much water, how many starting rations, and you set the simulation in motion for anywhere from 10 days to 2 years and see if your astronauts make it or not. And so it's a fantastic educational tool for grades 5. We have curriculum that we developed that's for grades 5 through 14. That's also next generation science standard aligned. And that curriculum has been used all over the world, and we're getting some really good feedback on that. There'll be an article coming out in the National Science Teachers Association later this year, early next year, entirely about CMOC. Pardon me? Remote access? Oh, public, yeah, it's available for free, absolutely. Absolutely, yeah. So this is an example of what I did during mission support. So mission support, I would download, I had a backdoor into the data that was being collected by CMOC Live, and every 12 hours I downloaded the data set and then wrote a narrative for the team, for the crew inside. So this was my second or third download, and they had some concerns about the CO2 levels, which never exceeded 2,700, 2,800, which is fine. It was, someone was actually standing near the sensor at that time. But this is the kind of narrative we're able to do with just that basic sensor array. And so it shows you, you can tell when they're waking up, when they're going to sleep. And I made these estimations based upon the time and the CO2 levels, and then sent it to the team and said, please confirm. And it was all spot on within about 10 minutes. And what's interesting is that these sensors are actually upstream from where they're staying. So there's enough back pressure, partial pressure from the CO2 to give you a really good sense of what's happening, even if the people are downstream from where the sensors are. And I'll explain the stream or the flow of air. So we're really pleased with how this worked. And so the modes of operation, depressurized, flow through, pressurized, sealed. Those are three modes of operation. The first two teams were principally pressurized flow through, which means we have an internal pressure, but we're also constantly passing air through. We're going to be designing and building our own CO2 scrubber from the ground up starting this fall. And with that in place, we'll have a large enough CO2 scrubber to manage the facility as it exists. The CO2 scrubber we have was not designed for the volume of the space, but it was designed for the quantity of people. And you have to meet both criteria to move the air through effectively. And then we did do two pressurized sealed experiments in the second mission where they seal everything up, they stop the airflow, and then they monitor the CO2 level rise just to see what happens over the course of 4 or 5 hours. And again, you could be inside for 3 or 4 days before you reach any kind of critical mass on the CO2. First aid kit and all the necessary medical equipment. Now we transition into the greenhouse. This is the original facility built by the Biospherians in 1986 and 1987. We had a very minimal hydroponics rack. We're now acquiring a full commercial set of hydroponics that will fill most of this facility. And our ultimate goal is to reproduce Linda Lay's 3-week stay in the space, but with hydroponics instead of soil-based systems. That's one of our principal objectives, and we're really excited. And Linda's on board helping us design and facilitate that. And exercise equipment. This was one of our rudimentary water filtration test systems. We'll be improving that. And now we go down into the lung. So there's a tunnel that you have to crawl through. It's about a 20-foot tunnel. If you're claustrophobic, don't do it. And on the other end, we have the lung. This is 4,000 pounds of steel floating on a cushion of air. And this is 1/10 the mass of what the real biosphere has, where it's 40,000 pounds floating on a cushion of air. You could do a whole lecture on physics on how this works. It's really, really cool. So this is what maintains our pressure. There's a there's a computer controlled, here's the top. So here's the top of the lung. This is the outside air, the other space. This is the inside. This is the outside. And this is how it's managed. So we installed a brand new blower with a computer control system and also a computer controlled valve. In the Biospherian days, they controlled everything from the outside. We wanted to give the crew the control, so we reversed it. We bought all new systems, put all the computer controls on the inside, which is shown on the left-hand side here. They can dial in. It's a variable frequency drive, which I won't go into the explanation of, but you have ultimate control, almost infinite control over the speed of the blower. So the part of the team's mission is to find that perfect speed of the inbound air that maintains pressure and maintains flow without overpressurizing or depressurizing. And that's part of their learning experience after the training. This magnehelic is showing at about 50%. This was during inflation or deflation. I took the photograph. We run at a nominal 1.5 inches of water, which is equivalent to about 1/10 of a PSI. And there are 6 magnehelics, 3 inside, 3 outside. So at all times, we always know we're pressurized, and it reminds people don't open the doors because you get a really big slap in the face. We use an internal air compressor sending air through an air manifold to the outside, and all of our EVA suits are then pressurized and run through that conduit, through that umbilical cord. Yes, we do have the capability of doing portable air as well, but for these missions to keep everything as lightweight as possible, the umbilical works just fine. And principal science objectives at SAM, I won't read all these to you, but our primary function, as I mentioned earlier, is the physiochemical to bioregeneration transition. We will be the first facility in the world to demonstrate, starting with the CO2 scrubber, and as the plants grow, seeing the reliance on and use of that CO2 scrubber diminish as the plants mature to the point where we may or may not be able to fully compensate, but we'll see that CO2 scrubber kicking on less and less as the plants reach the maturity. And then intentionally we'll harvest the plants and the CO2 scrubber will kick back on the next day. And we can also do, of course, crop rotations, staggered crop rotations to demonstrate that we don't necessarily need the CO2 scrubber if we rotate our crops in the proper succession, knowing their time from seed to maturity. So a little bit about the teams. This was Inclusion 1 and named Inclusion 1 and Inclusion 2 for good reason. Each of the teams had a fully blind person on board, and that really changed things for us. We learned a lot. I thought I understood what it meant to be blind. I had no idea. It was incredible to learn from Sherry. In particular, she came in 2 days early, toured the facility, and labeled everything with Braille, with the self-adhesive Braille markers, and gave me a long lecture on microwave ovens and toaster ovens and the rice cooker, and nothing I had bought it came anywhere close to what was appropriate for someone who could not see. So it was a very bold lesson, and we apologize profusely, but we also didn't know we were going to have a blind person on the team until 2.5 months before the team started. So we did our best, and we're going to compensate for that in the future. And they did outstanding. Sherry was just fantastic. So this is crew one with some of my staff in the background. The folks who have the jumpsuits and the patches, of course. And this is the day in which the very first team entered. Remember, this is the first time in 31 years that anyone's been inside of a sealed facility inside of Biosphere, or near Biosphere 2 on the Biosphere 2 campus. We had 4 television crew, 2 radio station, documentary filmmakers, about 65 people in the audience. It was a beautiful experience. It was really, really cool. So this is their entry. We had a little ceremony. We switched shoes. So they leave their outdoor shoes out. And we had special shoes for them that they wore on the inside, their HAB shoes. And on the right-hand side is Linda Lay, again, one of the original 8 Biospherians who lived inside for 2 years. And she was generous to be there and just gracious, just spent a lot of time with the team and really stood there for the welcoming as soon as they entered the airlock. And this is Sherry. I want to talk just about this EVA in particular. So in a pressure suit, not only, well, she's blind to start, she can't see, and in a pressure suit, there's so much air moving through. She can hear our people talking to her on comms with Trent and Matthias, but she can't hear her cane anymore. She can't hear the tapping. And so we saw her moving of her own accord with no guidance out the airlock, down the steps, across the concrete space into the Mars yard, which she had only navigated once before to practice. And she was whipping her cane back and forth, like fighting off lions. And we thought, wow, just smacking. And she didn't know she was doing it. We asked her later, did you know you were doing that? What is that? She says, no, I didn't even think about it. Because she couldn't hear, she needed the full tactile feedback. So she's whacking the rocks and the wood, but she did it. She made it. She navigated the entire Mars yard. And she even conducted a full sample return of her own accord. It was outstanding. And inclusion 2. So this is the second team. And Bindu in the middle. Bindu has also been a volunteer with Sam for about 6 months prior. So this really helped because she knew the facility inside and out, and just did an outstanding job as the team lead. And on the right-hand side next to me is Bernd Zabel. Bernd Zabel was the construction manager for all of Biosphere 2. He managed 2,000 people for half a dozen years in the construction of Biosphere and was in the second mission of Biosphere 2. And he now lives in Costa Rica and runs a resort if you ever want to go to Costa Rica. And just an outstanding individual. I really, really enjoy him. And of course, Linda Lay again on the left-hand side. So in the second team, we did something a little bit different. We extended the training. We realized that 1 full day of training, a 12-hour training session, was not enough. We now require a minimum of 18 hours of training. It's a technical facility and requires a lot of understanding the facility, of the gas exchange, of the CO2 levels. We go into the OSHA and the NASA standards for CO2. So the team members really understand what they're getting themselves into and how to manage those facilities accordingly. So this is the second team in training. And the second team was really, there's a lot of science objectives that they met, but I wanted to focus principally on the 3D printer. They assembled the 3D printer. Sadha's from Purdue University. She assembled the 3D printer within an hour and was already printing something by the close of the first day. They decided to do their official mascot, so they printed an astronaut. And then this was really cool. So I was sending these mission reports with data, and they found a way to print the data in 3 dimensions so that their blind crew member could feel the data with his finger and see the CO2 and oxygen and relative humidity and temperature levels with his fingers, which I thought was outstanding. And they did all of this, again, with no outside internet. They have only email. They have no Instagram, no Facebook, no web, everything. We shut off everything except email. So they had to ask mission support, please help us find this. We respond with 20-minute delays on every communication. And they just did outstanding work. This is Sadha's primary objective. She measured everything inside of the habitat, did all the measurements herself, and then created a 3D model again so that her colleague could feel, even though he'd already moved through the whole space, so he could feel the relationship between the different modules of SAM with his fingers on this 3D relief map, which I thought was just a brilliant idea. And just some photos from the second team's EVAs. We did 2 night EVAs. And Sada had to actually rewire. It's an old comms panel from the 1980s, but we used it as a demo. And she had to strip the wires, rewire it in a simulation of a downed comm system. She had to go out in the field and actually fix this unit. And they developed their own hand signals back to the airlock window. And before we do that, I'm going to switch just to the. How am I doing on time?
You're at 10 o'clock right now.
Oh my gosh. Okay, we're gonna have to skip the video. I apologize. Phase 4 development. So we are now for the summer. Matthias, Mason, Natasha, excellent guys in the back. They've been working. Matthias and Mason in particular with Sean, who's back in Chicago now. They were putting up with incredible heat. You guys noticed it was a hot summer. Even at Biosphere at almost 4,000 feet, they put up with a lot of heat and just worked all summer long to work on the refabrication of this building to install garage doors. Yes, those are pack rat nests, which Matthias, I think it took you a week to get the courage to actually get that stuff out of there. Yeah. And so then all the work that continues, and this is the same facility now just last week. And so now we're rebuilding the entire electrical system and preparing for the new Mars yard. And just real quick timeline, inspired in January 2018, initiated in February 2019, first funding, first pressure test, first teams. We built everything for $300,000, including labor. Yeah. And I want to thank Brett. Brett, stand up. Brett helped secure $1.5 million in funding. There are good lobbyists in the world. This is one of them. And just some quick photographs of the volunteers over the years. And that's it. I'm sorry, I went a little slower than intended. I went into the details. So all the people who made this possible. And these 2 hams in the back. Thank you. Oh, yeah.
Hi, Dr. Pandya. Can you hear me?
Yeah, I can hear you 5 by 5. Can you hear me?
Yes. You sound a little muffled.
Testing 1, 2, 3. Testing 1, 2, 3.
That's better.
Okay, perfect.
And you can go ahead and start your video as well.
It wouldn't let me a second ago. Oh, now it will. Perfect. Okay. Hi, here I am.
Hello. Do you have any slides to share?
I do. Let me get on top of that. Share sound, optimize for video clip, and here we go. All right, you should be able to see this now.
Looking good.
Perfect. Let me know when I'm good to go.
I'm going to give you just a quick intro. Hi.
Sure. Hello, how are you?
Good to see you.
Likewise.
Our next speaker, I'm very excited about. This is somebody I have admired and followed for some time. Dr. Shwana Pandya is Director of Medical Research with Orbital Assembly Corporation. She's also a scientist, astronaut graduate with the International Institute for Astronautical Sciences and Aquanaut with the Neptune mission. For her involvement with Project Possum, Dr. Pandya was part of the first crew to test a commercial spacesuit in microgravity. Dr. Pandya is also a licensed physician as a general practitioner. Prior to completing medical school, she attended Singularity University, where she co-founded CiviGuard, based on Singularity's challenge to positively impact 1 billion people in 10 years using accelerated technologies. Welcome, Dr. Shwana Pandya.
Thank you so much. Okay, so we have 25 minutes to talk about medicine for the moon, Mars, and beyond. So away we go. So you've heard a little bit about my background. I wear a few hats, and many of them will come into play this session, but we don't need to rehash the introduction. Instead, we're going to start with a question. Imagine that you were the crew physician for a long duration mission And as the crew doctor, you're asked to pack for that mission to the moon or Mars today. So the question becomes, what are you going to pack with you? So before you can answer that question of what you will pack, you need to know what you're packing for. And that includes understanding the hazards of the spaceflight environment. So this includes a whole laundry list of spaceflight hazards, everything from increased radiation to the acceleration and deceleration modes of launch to altered day-night cycles. So that is a 90-minute day-night cycle at the level of the ISS in low Earth orbit. That is a 14-day night cycle for 28 days at the lunar equator and just over 24 hours on Mars. You have to play nice when the extremely confined space. No one wants to be the astronaut that's voted off the HAB. That's always awkward. It's a psychologically demanding schedule. On the ISS, astronauts are scheduled down to the 5-minute mark. You have to trust the engineering of your spacecraft to keep you safe from the radiation, vacuum, and temperature extremes of space, as well as the atmospheric scrubbers to keep your atmosphere free of particulate matter and within habitable temperature and humidity and pressure confines. You have to trust the engineering of your spacecraft to keep you safe from micrometeoroid and orbital debris impacts. And of course, there's the everyday risk of lumps and bumps that you would encounter on Earth. And I haven't even mentioned the weightless elephant in the moon, which is, of course, weightlessness or microgravity. And suffice to say that every single bodily system is affected by the microgravity environment. Our bones lose density, our muscles lose mass, our fluids shift upwards. In long duration spaceflight, this can cause increased localized pockets of pressure, especially around the backs of our optic nerve, even leading to vision shifts in male astronauts preferentially. Our inner ears are confused, leading to a disconnect between what our eyes see, our proprioceptors sense about our position in space, and what our inner ears perceive as up versus down, resulting in space adaptation sickness for the first 24 to 72 hours in microgravity. And I'll spare you the image of what it's like to vomit in zero G, but suffice to say, it's not very pretty. And if you're performing critical activities like a spacewalk, vomiting in a confined space poses a very real asphyxiation hazard. And all of this so far is data from decades of human spaceflight in low Earth orbit. So now we need to ask the question, this being the Mars Society Convention, what happens when we go beyond low Earth orbit? And this isn't simply a theoretical question, because those of you who are invested in human spaceflight know that the international community led by NASA has very real plans to go to deep space, starting with Lunar Gateway. This is humanity's plan for humanity's first deep space station. So there are 20-year-olds alive today who have never known a world without a continuously crewed off-world spacecraft in the form of the ISS. And my hope is in 20 years, it'll be totally normal for 20-year-olds in 2040 to just think it's totally normal to have a deep space Lunar Gateway space station. Differences between Gateway is that it's smaller. It will not be continuously crewed. Its mandates are to serve as for science, for Earth observation, solar observation, lunar observation, and deep space astronomy, as well as serve as a way station on the way to the lunar surface, of course, for Artemis. So Artemis, as most of you probably know, is humanity's plan to send the first woman, first man of color, and next person to the moon. Jeremy Hansen will be Canada's first astronaut to go on a cislunar journey with Artemis 2. And the Artemis mandates serve to establish permanent surface lunar operations, serve as a point for exploration, science, in situ resource utilization, and of course, serve as a test bed for Mars. So now, we'll need to start talking about, well, what are the challenges about sending humans to deep space? We have limited data, but we have some data from the Apollo missions. And we know from that deep space, that lunar regolith was a very potent skin, respiratory, and eye irritant. It was very fine and it clogged up the EVA suit joints. So for those who have heard of the moon landing must be faked, please know that they must have spent a lot of effort faking the moon landing, because there are hundreds, if not thousands of pages of documentation dedicated to lessons learned from Apollo, from EVA suit recommendation improvements to biomedical lessons. So lunar regolith is just one consideration for deep space missions. Also consider that the nature of EVAs that we're performing now are totally different. From performing a spacewalk in microgravity outside the ISS, now we're proposing to perform spacewalks in 1/6 gravity on the moon, as well as 1/3 gravity on Mars in a steep, dusty, challenging, jagged terrain. Imagine if you fall into a crater. Now the challenge for trauma or the potential for trauma and the need for astronaut rescue in a challenging environment becomes greater. There's also the challenge of radiation, which I alluded to briefly in the very first few slides. And the bottom line is the further up you go, the higher up you go, the more radiation there is to contend with. So at the level of the International Space Station, within the confines of Earth's Van Allen belt, we're still relatively protected from higher energy ionizing radiation in the form of solar particle events and background galactic cosmic radiation. By the time you get to deep space outside of the Van Allen belts, either to a lunar or Martian mission, you are exposed to 750 times the equivalent of radiation of what you would expect on spending one day on Earth. So at the level of the ISS, you're exposed to 250 times of what you would be exposed on Earth. So that's a threefold difference. And that's a very real consideration when we talk about annual and lifetime limits for radiation exposure to astronauts. So the last part is the distance. So for those of you who are Douglas Adams fans probably know that Hitchhiker's Guide to the Galaxy quote that says, space is big. Space is so vastly, hugely, mind-bogglingly big, you wouldn't believe it. And the same applies to space. So when we talk about the distances involved with deep space travel, whether we're talking about Earth-Moon travel or Earth-Mars travel, even traveling at the speed of light, telecommunications are delayed. So it's about a 2.4-second round trip delay to have a conversation between Earth and Moon. And depending on the alignment of Earth and Mars, it can be a 6 to 48-minute round trip delay, depending on the source you look at. So now imagine that you are a physician on the Moon or even Mars, and you have a massive medical catastrophe. You don't have time to radio back to Earth for help. So when we talk about this laundry list of challenges for deep space missions, we talk about this as the bridge framework, or to summarize, radiation, isolation and confinement, distance from Earth, altered gravity, and everything else which falls under hostile environments. This includes the lunar dust that we talked about, the altered day-night cycles, and the altered operational stress of the schedule of the astronauts. So if you remember nothing else from this introduction to deep space medicine, it's simply that space is trying to kill you. And so to qualify that a little bit further, space is hard, space is expensive, and space is trying to kill us. There's a lot of risk involved, and our job is to learn to retire risk prior to sending astronauts into this high-risk environment. So how do we do that? You just saw a great presentation from Kai about how the biosphere can be used for mission simulation. And in this next session, in this next section of this talk, I'm going to take you through my own experiences in space-like environments. And to start, we're going to kick this section off with a question. So that question is, what does the International Space Station have in common with a remote village in Kenya, an underwater research habitat, or a polar medical deployment? And the answer is they are some way all analogous to the spaceflight environment in that they're remote, resource limited, isolated, confined, or all of the above. And so that's why we call them analog environments, although I'm sure you all already know that. So the next question is, how do we use these analog environments to prepare us for space? So it depends on the type of analog environment. So we can emulate altered gravity environments in parabolic flight, otherwise known as the vomit comet. By falling at the same rate as the airplane, we can generate periods of 20 seconds of microgravity. And it's no different than if you're cresting a roller coaster in an amusement park. When you come over the peak of that roller coaster, your heart lifts into your chest for a brief second, and then it's because you're weightless and you're falling at the same rate as your vehicle for that split second. So I can keep telling you what it's like, but I'd rather show you. Here's a snapshot of us, a video of us testing spacesuits in microgravity with the National Research Council of Canada.
fast so that I can record it.
No rain in the back, though? Not rain in the back. Umbrella?
So, Adam, I will get the billboard back.
So you can see we work as very finely tuned, well-rehearsed teams in a very closed operating space. We all need to know how our communications work. And the other thing that I'll add is that it is a lot of fun to be in a spacesuit in microgravity. It's impossible to be in an IVA suit and not have a giant smile on your face. If you ever have the opportunity, I highly recommend it. But you might be saying, but Shauna, that's only 20 seconds. That's kind of limited, isn't it? And I'm glad you mentioned that point. So as every type of analog environment we bring up, there are trade-offs. So you are limited to 20 seconds. So if you require science that requires a little bit of a more extended period, you may want to look at other gravity analogs. So for example, this is a snapshot of the gravity offset machine we also have at the International Institute for Astronautical Sciences. And this is a partnership that we did with the Canadian Space Agency in 2019 in their lunar high bay. And basically, with the gravity offset, you could input what percentage of your own weight that you want to offset, and then simulate prolonged periods of altered gravity. So in this case, we have offset 99% of my own body weight. So I'm simulating fixing a panel outside the International Space Station in microgravity. You can also offset 83% of your own weight to simulate 1/6 lunar gravity, or 62% of your own weight to simulate Martian gravity. Of course, there are trade-offs again. So only what is within the harness is offset. So you can notice that the cables I'm working with are still subject to 1G and would fall down if I were to let them go. And of course, at the very beginning, as one of the hazards of spaceflight, I mentioned the increased Gs of launch and landing. So we need to also know what human physiology does in increased gravity environments. Centrifuges are one great way to do that. So this is a snapshot from our time at the NASTAR Centrifuge Center, where we took part as medical subjects in the study. We also learned a lot about living and working both on top of and under the water. So again, from our work at IIAS, we simulate off-nominal emergency egress operations out of an Orion capsule. So that's a fancy way of saying crash landing or something has gone terribly wrong. And so in this case, we simulate either a toxic gas leak exposure, fire or smoke in the capsule, and have to simulate egressing from the capsule, either topside or side hatch, into the water and up into the emergency raft. And we have to do so as a quick coordinated team. I can tell you, I learned the hard way, it's very important not to get water in the suit. You're still buoyant due to your portable flotation devices, but it just makes your task climbing up into the raft monumentally harder. I talked about living and working under the water. So this is a neutral buoyancy lab. You may be familiar with the concept. NASA has the world's largest NBL at 6.2 million gallons. It's able to fit a near entire life-size replica of the International Space Station underwater, allowing NASA and CSA and ESA astronauts to rehearse their EVAs from start to finish underwater. We have a baby NBL in Groton, Connecticut. We are able to simulate spacewalks from start to finish in runs of 45 to an hour plus lengths of time. We're working as a dedicated team of 2 EVA astronauts, communicating with topside support, maintaining our life support through our umbilicals. We have to clamp ourselves onto a structure at all times, so we're tethered to either the airlock, the outside of the spacecraft, or the strut. We have to navigate towards the near field to swap out a dysfunctional panel or a dysfunctional module that you can see here in the bottom corner of your screen. And it is exactly, once you achieve your neutral buoyancy, it feels exactly like you're weightless. I still have dreams of being out there, and it really does feel like you're in space. I talked about working and living under the water. So you heard in my introduction that I'm an aquanaut. I've earned this designation over 2 underwater missions. So this is where you are living and breathing air at the same ambient pressure as the water around you. So we earned our aquanaut designation at the Jules Undersea Lodge at 20 feet of depth in the Florida Keys, first in 2019. And then again in May of this year. Neptune, like everything else in space and exploration, is an acronym and stands for Nautical Experiments in Physiology, Technology, and Underwater Exploration. There will be a quiz on that at the end. And basically, we worked as a crew of 5 for 5 days the first time, 6 days the second time, to perform key experiments in science, biomedical technology, and technology demonstrations. And basically, we found that the mission wasn't long enough. We were really proud of the work that we did, and I would do it again in a heartbeat. And in fact, NASA does the same thing with their astronauts just down the road from Jules, where they send their astronauts to the Aquarius reef base, 13 miles horizontally distant from Jules, but at 60 feet of depth. So you may have heard of this referred to as the NEMO missions. I was there, and in 2019 as part of my dive medical technician training. And so we did not go in saturation. So we just stayed at surface pressure, but it is an incredible little place. It's the size of a school bus. And as the fish swim by and stare at you curiously, you wonder which one of you is really in the aquarium. So NEMO stands for NASA Extreme Environment Mission Operations. And again, the NASA astronauts / aquanauts work on their team dynamics, their communication, and also carry out protocols, procedures, and science. The key difference of being at 60 feet of depth. So at about 20 feet of depth, Jules, you're essentially at surface pressure. There's no, other than a safety stop, there's no significant decompression time. If you're a diver, you know that once you're at a certain depth, you have to surface at a set rate to let the dissolved nitrogen bubbles in your bloodstream come out of solution at a fixed rate, because if they come out too quickly, they could form emboli and cause joint pain, or in worst case scenarios, seizures, coma, or even death, which I don't need to tell you are bad. So the decompression time at a place like Aquarius is 16 hours and 47 minutes. So if there is an emergency in the habitat, the crew needs to work around that decompression time or accept the risks of surfacing too quickly. By comparison, so that's nearly 17 hours. If you have a stat evacuation call on the ISS and you escape to Earth in a Soyuz capsule, for example, you could ostensibly perform that evacuation in 3 to 6 hours before you definitively reach medical care. So you can actually get to definitive medical care from space faster than you can from the Aquarius reef base. Valuable what we learn from these types of analogs. I don't need to tell you that there's many Martian and lunar analogs out there. This, of course, is the Mars Desert Research Station, where I was lucky enough to be both a crew medical officer and in my second tour, a commander. And it really is as if you are living and working on Mars. You bring your experiments, your crew dynamics, your mission objectives with you. If you suit up, if you go outside, you have to suit up, lest the environment kill you. And you're privy to these amazing, sprawling vistas that really, truly make it feel like you're conducting your EVA on Mars. Cinder Lake, just outside Flagstaff, Arizona, is another example of an analog, of a geologic analog. In this case, a lunar analog. So this is where the Apollo astronauts performed their Apollo training. What NASA did was detonate, set off some explosives and create crater-like formations in this lake dry bed of a lake. And it really does feel like you're on a lunar surface out there. So it's an excellent training grounds for performing geologic campaign in northern Canada in 2017. We are in a unpressurized research vehicle at 19,000 feet, hence the oxygen masks. The crew dynamics and human performance elements are very critical. It's myself as the payload specialist, the mission specialist, and the research pilot in the aircraft. And we're testing, myself as the payload specialist, I'm operating this tomography instrument that you see over my right shoulder, trying to get more information about the three-dimensional structure of noctilucent clouds while we're up in that craft. So the communication becomes really important. In my own space medicine class, we don't go to the middle of nowhere. We do go to the wilderness, and we simply take resources away from our students with the goal of turning them into a space medical MacGyver. So most of the students who come to the class have no medical background, and our goal is to give them a standard set of skills to turn them into give them the ability to perform assessment, triage, and treatment in a resource-limited environment, be it a wilderness environment or a space-like environment. So as we get to the last 5 minutes in this presentation here, let's talk about the value that we derive from this type of work. What kind of research and innovation can help inform us for human spaceflight and especially exploration class missions to the moon, Mars, and beyond? So I've talked a little bit about the value of analogs already, and we published and presented on them extensively. We've also used these environments as test beds for key technologies. So for example, in the middle panel, you can see earlier this year, we presented on our work on testing portable, lightweight, non-invasive biomonitoring patches in a microgravity environment during parabolic flight. We've also tested virtual reality medical modules in parabolic flight to increase their TRL or technology readiness level. We can also perform research about emerging concepts in space. So here is a literature review on medical guidelines for commercial suborbital spaceflight that myself and one of my research teams performed. Other areas include psychological resilience in long-duration spaceflight and the logistics of reproduction and sexuality in long-duration spaceflight. I won't keep you in suspense, but the one-line summary of that research is that further studies are required. So let's talk about technologies and innovations that can enable humans not just to survive, but thrive on exploration class missions. And I'm going to take you through 3 ventures that I'm involved with in my last few minutes here. So we know that food, you may have heard this throughout the conference, is a significant issue, both in terms of palatability, being lightweight, having nutrition, having texture, having flavor. Having a long shelf life. So one of the companies I work with is called Astrius. I serve as their medical advisor. And the best part of this is it's chocolate that's good for you. So it has a long shelf life. It's non-crumbly in microgravity, and it's infused with your recommended daily intake of vitamins, as well as nootropics to enhance cognitive performance. And my favorite version is a caffeinated version. So this helps with the shelf life and palatability and nutrition component. And the company has also partnered with Aleph Farms in the NASA Deep Space Food Challenge previously. I also serve as the medical research, strategic research advisor to Above Space, formerly known as Orbital Assembly. And we've talked about the challenges of living and working in microgravity for prolonged times. So you might be saying, well, why not? But can't we just bring gravity with us? And I think that's an excellent suggestion. Straight out of Space Odyssey 2001, we can use simple physics to generate gravity. That's a simply the rate of rotation squared over the radius of the space station can help you generate artificial gravity. There are side effects, of course. There is gravitational cross-coupling, Coriolis effect, as well as height gradients. However, this may help solve some of the deleterious changes, or address them at least, that we see in long-duration spaceflight and microgravity. And of course, coming back to virtual reality, I also currently I serve as one of the executives with a Canadian company called Luxonic Technologies, and we leverage virtual reality, mixed reality, and 3D 360 video to help. And we've previously built virtual reality modules for astronauts on long-duration spaceflight, and we've been funded by the Canadian Space Agency to do so. So in summary, to help humans survive and thrive on Mars and beyond, we're going to have to science the space out of this. So in the last minute here, let's bring it back to Earth. You might be saying, but what has space done for us lately? And I'm glad you asked. One of my first publications was looking at medical innovations from space that have benefited everyday life on Earth. And there's a very long list. And especially knowing that up to 44% by water filtration devices used to bring clean water to Kenya. We've seen atmospheric scrubbers be used in the produce transport chain to increase the shelf life of produce. We've seen solar arrays power the vaccines and refrigerators for areas without electricity. So coming back to this idea of virtual reality for space, we use it for areas that are infrastructure limited, resource limited, that require low mass, low volume, low power. And that actually sounds a little bit familiar because in the COVID era, so many of us lost access to our traditional physical and educational workspaces. And in fact, we have also used our virtual reality technologies to develop certification and educational modules for paramedics on Earth, for example. And more recently, we've been funded by the Canadian Space Agency and in the final rounds of the competition for developing a point of care ultrasound that is in mixed reality. Here's me testing it in the Arctic Circle, as well as on an underwater mission. And the importance of such next generation technologies for resource limited environments really hit home to me when I was in Ukraine last summer on a medical deployment. And the bottom line is there's a whole world of challenges out there, and there's a lot of good to do. And it starts with a single step, and it starts with us. So thank you very much for your attention, and I will turn it over in case we have time for questions. This is my contact information.
I think we got time for maybe one question. Yeah, go ahead, Jack. Microphone's right behind you.
Yeah, I need a mic. Thank you. Okay, my wife is a physician. Long ago, I went through residency fellowships with her, their whole routine, getting board certified. A young person comes out of med school. They finish their residency. They want to make a life in aerospace medicine. Is there any fellowship available right now where they can pursue that?
Yeah, absolutely. So you are currently in Arizona. Is it safe to assume you're American?
Oh, we live in California, but I mean, you know,
yeah. So the distinction is important because aerospace pathways to aerospace medicine are country dependent. So within Canada, there's no formal aerospace medicine board certification except through the military. I actually don't have mine. I practice emergency medicine. In the States, there are many excellent aerospace medicine fellowships through the University of Texas Medical Branch. That's where a lot of the NASA flight surgeons claim their heritage, through the Mayo Clinic, and more. And what's really exciting over the
Oh, we lost the.
We lost your sound there, Dr. Pandy, but we're out of time. Thank you very much for your appearance today. It was fantastic.
Okay, thanks. Sorry about that sound. All right, all the best. Bye.
Thank you so much. Enjoy the rest of your day.
You there? I'm going to give you this one when I'll do your intro. I'm going to give you this one, and then I'll help clip it on you. All right. Next up, we have Dr. Sarah Walker, who is an astrobiologist and theoretical physicist interested in the origins of life and how to find life on other worlds. She is most interested in whether or not there are laws of life related to how information structures the physical world that could universally describe life here on Earth and on other planets. Walker is Deputy Director of the pioneering Beyond Center for Fundamental Concepts in Science, which is devoted to confronting the big questions of space, science, and philosophy. She also co-founded the astrobiology-themed social website, saganet.org. Check it out. And on the board of directors for Blue Marble Space. She is active in public engagements in science with appearances at the World Science Festival on Throughout the Wormhole and NPR's Science Friday. Welcome, Dr. Sarah Walker. All right, James is grabbing your thing. You want to hold it or would you like to flip it?
I can clip it. Hi, how is everybody? Good. So I'm only here this morning, but already it's been a lot of fun. I think we're still waiting for my slides to come up. So yeah, it's all right. Yeah, so just to sort of give a little bit of background, I think my talk is probably going to be a bit more abstract than some of the others, primarily because I'm really interested in abstract and foundational ideas, but I have a very deep conviction that life is a very interesting and fundamental phenomenon. Obviously, looking for it on places like Mars is a pretty profound question. So what I wanted to do today is actually talk about prospects for life detection on Mars, but connecting it to some deeper ideas about the nature of life in the universe and some things my lab and collaborators are thinking about, and also how this might tie to if we don't find life on Mars, can we actually seed life on Mars and can we make it a living world? And I wanted to just kind of give a preface about my background and my thinking. So I think there's a couple things that I think about in the way I approach these problems that are maybe different than the reference frame of other people. One is that I really do have a pretty strong conviction at this stage in my career, although I'm happy to change my mind at any time. That life is a planetary scale phenomena. So we really need to think about life in terms of biospheres. Thank you. And the second one is that life is a pretty fundamental phenomena. So I think a lot of people think in terms about detecting life because we find a molecule life uses on another planet, but I'm actually much more interested in looking for a general process of how planets build complexity. And so these ideas of life being planetary and also thinking about open-ended evolution and complexity are kind of deeply ingrained in my work. So that's just sort of to give a little bit of background about the frame of reference. And as I said, my talk might be a little bit more abstract than some of the other ones. I'm so interested in the applications and the practical technical aspects of the work, but I have a tendency to want to think more about sort of the abstract big ideas. So I'll try to connect to some of the technical work that we're doing also, and some of the kinds of measurements and experiments. But for me, being an astrobiologist, I think there's one central problem of astrobiology, which is we don't know how much life is out there. And obviously we have brilliant targets in our solar system like Mars that we might actually use as scaffolds for trying to detect life and trying to understand what the likelihood of distribution of life is in the universe. And usually people don't actually put life on kind of a missing component on a cosmological diagram, but my original training was actually in cosmology. And as I mentioned already, I think that life is a pretty fundamental phenomenon in our universe. And I want to talk about it at that level, because I think when we're thinking about life detection, we haven't really been having an adequate enough discussion about the problem of what we're looking for. And I'm sorry that this is a little bit hard to read, so I'll read the quote aloud. This is from a pretty seminal paper on defining life by Carol Cleland and Chris Chiba in 2002. It was literally called Defining Life, where they say, in the absence of an analogous theory of the nature of living systems, interminable controversy over the definition of life is inescapable. And so probably, I know there's been a lot of life detection talks already at this conference. And, a lot of times what ends up coming into debate is what we're looking for actually going to be definitive of life or not? Or in the case of looking for things like life on Earth, is this actually going to be something that would be product of a biosphere on Mars, for example, or product of biology on Mars? So this issue of defining life is very challenging. It's obviously widely discussed. And so this is sort of a canonical definition of life that you might read in a biology textbook. It's a system capable of performing any number of functions: eating, metabolizing, excreting, breathing, moving, growing, reproducing, et cetera, et cetera. So usually when you read a biology textbook, they give you this sort of list definition at the first chapter. So Carl Sagan had this really brilliant essay, also titled Defining Life, a bit earlier. It was published later, but he made the point that that kind of definition includes things that we might want to exclude, like cars. So cars would satisfy that definition. And now cars have been to space, so maybe we really do think that they're an example of life. We're not sure. So this kind of points out this sort of challenge we have when we're trying to think about definitional descriptions of life, that there's always these challenges. So Carl Sagan points out that, the properties we just listed are present in machines that no one's willing to call alive, or absent from organisms everyone's willing to call alive. And if you dig in the literature, any definition of life has these sort of boundary cases. This is why everybody always debates viruses. And for me, I think it's just pointing out a fundamental issue that life is not like a thing that you want to draw a hard boundary around. It's not this thing's life or this thing's not life, because you can't cleanly categorize it. And so this suggests that the way we're thinking about life is not an objective category of nature. It's not a natural kind, as philosophers would say. So we have this sort of issue that we need to figure out, like, what is the property that we're actually interested in talking about. And obviously at this meeting, we're keenly interested in Mars and the potential for life on Mars, either in the past, either there now, or in the future, as we might exist on Mars. And we have one example of a world that we know that has life on it, which is our own Earth. So what is fundamentally different about these two worlds, if anything, from the perspective of thinking about the nature of life in the universe? Are they both living worlds? Is one dead? Is one alive? Now, the what is life question to me is more interesting when you try to move past this idea of defining life and you try to look for more fundamental principles, which I've already said. And I think this is a sort of long enterprise in my field of theoretical physics. People have been thinking about this for a very long time, and it's obviously a super hard question. But usually when people are thinking about it, they're focused on defining life in terms of an individual organism. And I think this is one of the places that we have kind of failed, because again, it's this idea of drawing a spatial boundary. So obviously viruses would be sort of, the canonical challenge point to that, but there's actually a lot of reasons that you might not want to think about life in terms of an individual cell. And Erwin Schrödinger, when he wrote his famous book, What is Life, thinking about this problem and trying to actually address this question about how we can account for what happens in a living organism in terms of physics and chemistry, came up with the idea toward the end of his book that it might require other laws of physics. And so this is sort of my general framing of the problem, is that we're not really thinking about the structure of life the right way. People trying to theorize about, a fundamental unit of life is not capturing the right kinds of regularities. There probably are some missing principles that allow us to understand the transition from non-life to life, but they might be much more general and much more abstract than that. And so the idea I've been working on with a number of colleagues over the last several years is this idea that life is really about how complexity gets built up on a planet, if you want to think about it as a planetary process. You can also think about it in terms of information, how information actually builds physical structures. You can think about it in terms of evolution. So maybe life is just any process that undergoes open-ended evolution. But there's a lot of sort of different ways of framing it. And the question is, can we actually capture this kind of regularity? So instead of thinking about life as an individual, can you think about life as a process that happens and builds structure over time and carries some of the structure that's been built in the past all the way up to the present? And so I think this visual is quite different than the way people usually think about trying to define life. I think about life as the entire structure of the biosphere from when it emerged on our planet all the way up to the present day, and when it eventually replicates off planet, for example, if we start producing life on Mars and we start building through technological infrastructure, a reproduction event of our biosphere happening on another planet. So if we take the idea that life is a process that builds complexity on planets, so far we only know of one planet that's undergone that. So this is sort of an abstract depiction of some of the complexity that's been built on our planet over several billion years of evolution. And then the question becomes, can we discover life-like complexity on Mars? Is Mars doing anything that might be considered to be something that could only be produced by evolution, or could only be produced by an information processing system, or is in the realm of whatever it is that we might call complex? And this challenge is also very hard. So none of these questions are easy, but there are ways of thinking very concretely about this once we start thinking about the chemistry that's generated on planets and what kind of chemistry is possible. And so this is sort of what I'm going to be talking about for most of my talk, is actually how we can think about this problem. And it leads naturally to the question about whether we could detect whether life on Mars exists by looking for chemical complexity, for example. And if it doesn't exist there, can we actually induce the planet to have an origin of life event? Now, an origin of life event on the planet might actually be making Mars come to life by some geochemical process and being able to understand the origin of life enough to induce the planet to actually transition to having an evolving process on it that emerges individuals and ecosystems and eventually all kinds of life. Or it might be that we actually build the kind of technological infrastructure that we've already been hearing at this meeting. So I'm going to be talking now. So that's sort of just the intro to like the framing of the problem and some of the philosophy about how I approach it. But I want to talk concretely about this idea of doing life detection with a foundational theory that tries to understand how we talk about complexity and how we talk about it in terms of the chemistry that life produces. And so this is actually, I was debating about what I should talk about today, because I could talk about all kinds of things about planetary scale life, and chemistry is biochemistry is a planetary scale phenomena. But I really want to talk about this one because it's actually very timely, because we just had a paper out this week in Nature on the theory, and George Ellis wrote a wonderful review of it, which I can point you guys to, which kind of connects the work we're doing to some other foundational literature on the physics of evolution and how we can think about what life is doing. So for those of you that might know, I think sort of some of you might be familiar with Stuart Kaufman's work and the idea of the adjacent possible and how the biospheres explore complex spaces. So we're in the same kind of space of ideas as Stu, and I've actually taken a lot of inspiration from his work, but I think some of the things that assembly theories offers is it's a much more physical theory, and you can actually talk about these properties in molecules. So just to kind of preface the direction I'm coming from thinking about this. So I was trained as a physicist, obviously. So I'm well aware of the fact that space is big. And I remember thinking when I was a PhD student about, point your pencil and like there's 10,000 galaxies at the tip of your pencil in the night sky, if you follow that line. So I think we all have a sense that the universe is very big. Right. And of course, in this meeting, I think you all have a clear sense of it because you know how far away Mars is, how hard it is to get there. And that's, one of our closest planetary neighbors. So we have no problem at this day and age thinking about the universe being physically large. Where it gets kind of interesting is we don't really think about the universe being chemically large or what that even means. And so this is a sort of a graphic showing formation of the molecule Taxol, which is an anti-cancer drug. It's something that is a product of biological evolution. It's formed in plants. And I'm always sort of fascinated by the idea that chemical space actually hasn't been explored. So if you go into the cheminformatics literature, we have estimates, I think, of about 90 million molecules that we know of and have characterized or have some idea of their properties in the sort of chemical literature. But chemists estimate that there's about 10 to the 60 molecules that are probably about the size of 2 amino acids stuck together. 10 to 60 is a really big number. And part of the problem of understanding the transition to life is that life is actually exists in chemistry. And if you get to anything above small molecules, chemical space is larger than the universe can explore on a single planet. It's actually larger than the universe can explore on all planets. We can't actually, there's no possibility of using all the resources in the entire universe to make one copy of every possible molecule. We don't even actually know how to talk about that problem. It's kind of crazy. The reason that it's challenging, though, is because it's not like you can look out and take a picture like we can with Hubble. This is sort of a potential space. It's a space of things that could be created on planets. And planets, in some sense, are the generators of chemistry. They make the most chemical novelty. And the first place that we see that as being kind of something we think is significant is when a planet evolves something like a cell that suddenly has these very large macromolecular structures that seem absolutely impossible because they exist in this chemical space that is so combinatorial large that you couldn't even possibly imagine why that particular structure exists and not all the others. And of course, we know why that structure exists in all the others. We call it selection. But the question is, how do we actually formalize thinking about that in terms of the structure and the physical properties of these molecules? So one question you might ask is, what's the likelihood of a very complex structure, a molecule like Taxol, forming from the periodic table of the elements on any planet in the universe? And I would say it's zero outside of evolution. Most people would say, oh, there's a small but finite probability that a geochemical system could fluctuate any molecule into existence. And in fact, this is sort of the canonical explanation for the origin of life that some people accept, is that life can spontaneously fluctuate with all the complexity. And it's not a sort of cascade of selective processes that are gradually building up more complexity. And so I guess part of the conjecture, part of the hypothesis that we're working on is it's evolution all the way down, but we need to understand what that looks like in terms of the molecules that are selected and how they build further complexity. So thinking about molecules is obviously very abstract. And for most of us, we're not trained in thinking in terms of molecular bonds and what kinds of molecules are possible. I'm certainly not an expert in chemistry. And so I think it's a little bit easier to talk about other assembled objects or other complex objects that exist on this planet in terms of thinking about the possibility space, just for our ability to imagine them. So these are all the pieces that are in the Hogwarts Lego set. I think there's something like a couple thousand pieces of Lego. So imagine I actually brought it with me. I should have done that actually, but I could have just dumped all the Lego on this table and I could have asked you to just start putting pieces together at random without instructions. How many people here think that, you know, all of us collectively could have built Hogwarts without the instructions? Does anybody think we could? Yeah, maybe. Maybe some people, but you have an idea in your mind of that object already, right? If I just was shaking the table and we were watching pieces randomly assemble, do we think that we could do it? Probably not, right? So this is a pretty complex object. And so one of the questions that we have is, what is the likelihood of this object forming in the absence of evolution? And so something like Hogwarts, I think if you were sitting here shaking the table from now until the end of the universe, if the universe has an end, it would probably never happen. Yet this Lego object is something that exists on our planet. And in fact, it exists in high abundance because lots of children and adults have this Lego set at home and have built this Lego set. So why is it that this object can exist in high abundance? It's because it was selected to exist and it's built, you know, there's a lot of information in our biosphere that goes into building something like this. First, Lego was invented. Second, we've had castles on this planet for thousands of years. Third, there was a very popular book written that had a castle called Hogwarts in it. So all of that information aggregated in this particular object. And so one of the ways that we want to talk about how do we actually think about how unlikely an object is if we actually did sit here and we were putting the pieces together to build it, we could look at all of those sort of pathways that we actually built it. So imagine I'm sitting here and I take two pieces, I put them together. I take that piece and I add a piece. I take that piece and I add a piece. And all of those pathways build up to that object. There would be a shortest such pathway. And this sort of bounds the minimal amount of time in terms of construction tasks, building operations to build that particular object. I could also do the same thing for molecules. I can break a molecule apart and I can look at sort of what's the minimal set of operations that are recursive. So they use parts I built already to build that object. And this is actually a really important concept when we're talking about the complexity of objects from an evolutionary perspective. And this is a foundational feature of the theory that we're building, is that objects can be decomposed into parts. And when you look at the assembly of those parts in terms of the minimal number of steps that retain memory of objects you built in the past, there should always be a minimal path length. And that bounds how likely, how easy it is to produce that object in the absence of information specific to assembling that object. So Hogwarts would be really hard to build because it has a really long path length. That's why we don't expect it to spontaneously fluctuate out of those Lego pieces. But if I had asked you what's the likelihood a beige piece is going to stick to a pink piece, that's probably going to happen, right? So that's not an object that requires a lot of selection and constraining of the space of possible objects to form. It's one that's pretty easy to form. So we have a way of formalizing this for molecules, this sort of concept. It's called a assembly index. And so basically you can count the minimal number of bond forming operations to assemble an object from elements where you're using parts you've made before. And so this sort of feature is very important in the way we talk about evidence of selection. Because if we look at a whole bunch of complex objects like this blue one, this green one, and this red one, they have different numbers of steps to produce them. So imagine I'm talking about all possible molecules now. And I want to talk about how hard is it for the universe to make any one of these possible molecules. What this idea of this assembly index, this minimal path gives us is it gives us a way of ordering objects by how difficult, how much selection or constraining of the space of possible objects is necessary to make that one. So if you think about Hogwarts, it would be way up here in this sort of number of steps to make it. And it exists in this space of an almost uncountable number of objects. It's actually iteratable, but like imagine all castles you could build, and then imagine all pieces, all Lego constructors you could build that have, you know, all the same pieces as a Lego Hogwarts set. And then imagine that you've violated the rules of Legos and you're just gluing them together. And there's like a lot of structures. So what we try to do is actually talk about ordering objects by this sort of evolutionary path, like how many steps to build them. With this sort of unconstrained space being the one where you have no rules and you don't care. So there's just all combinations of possible atoms or all combinations of possible Legos. And then as you go into this sort of inner structure, you actually start having objects that have a historical contingency to them. And there's only some things that can be made, because every time you select a structure, you're constraining the space of future possibilities. And so this is one of the reasons that I think the universe can even build any complexity at all, is because all the complexity is historically contingent. Everything that is built on this planet now is dependent on the 3.8 billion year history of life on this planet. And so we actually naturally built that into the structure of molecules. Every single molecule you build is based on parts you built before. And if you follow any reaction sequence, you don't invent new structures in molecules, you're just reconfiguring them. So there's this historical contingency in what gets built. So the idea being that if we can think about complexity in this way, complexity in terms of how hard is it to build an object, and then ordering objects, so they have sort of an evolutionary depth in some sense as a physical feature of the object, then we can talk about evolution building up more complex structures over time as sort of a meaningful physical feature of those structures. So for molecules, you know, we can talk about this pretty concretely. We're thinking about it for other kinds of structures biology has created, including technology and tissues and all kinds of things. But a critical feature here is that if you're thinking about, so I mentioned this 10 to the 60 number about like possible small molecules. Now it's interesting, like if you look at meteorites, we know meteorites have a lot of complex organics, quote unquote complex. What we really mean is it's complicated because there's a whole bunch of stuff that we can't actually differentiate what it is because it doesn't exist in high abundance. So there's a lot of carbon compounds, but, and you can also see this if you look at like the foremost reaction, unconstrained, it's an origin of life reaction, or a reaction studied often in origin of life science. If you leave it unconstrained, you make a ton of stuff. And I know Steve Benner was here. He's, you know, sort of famously talks about the tar paradox in the origins of life, which is a great way of paraphrasing it. So one of the issues is if you have a completely unconstrained system, I'm shaking the Legos on the table, it's just going to build a whole bunch of random stuff, and none of it's going to be in high abundance, and none of it's going to be very complex. And so we have this sort of idea that you know, if you just have an unconstrained system with no selection, it'll exhaust sort of a low complexity chemical space. In order to get it to build up to high complexity space, you have to start reusing parts, and you have to start building in a particular direction along a particular trajectory in terms of the possible structures. And that's where the historical contingency and selection starts to matter. And it turns out that if we can actually formalize a transition in these assembly spaces where it is unlikely in the absence, actually it's impossible in the absence of selection and evolution to ever observe an object in high abundance above a certain threshold, above a certain number of minimal steps. So, and that minimal steps has been empirically validated. I'll show the data in a minute at about, I'm going to skip ahead actually, because I want to be able to get to the data. I didn't realize how slow I'm going. Sorry. So if you're thinking about, hang on one second. What time do we actually start? Just so I know how much more time I have. 5 minutes. Okay, perfect. Thank you. Sorry. All right. So what I want to talk about here is just this sort of idea of how we actually measure these number of steps in molecules. And it turns out that you can do it with a mass spectrometer. So, so if you're imagining what I was talking about with this threshold, this idea of a threshold, if you're trying to build up molecules randomly, you're just going to exhaust low complexity space. And so we had this conjecture that if the molecules were above a certain assembly index, that we wouldn't observe them outside of life. And this is just showing how we can actually measure this feature of building up a molecule with a mass spectrometer. So it's actually empirically tractable. And so this paper came out now 2 years ago, but basically what the main result of it was is if you survey a bunch of biological and non-biological samples, and we had some samples that were blinded from NASA, including meteoritic samples, we don't find any molecules that are produced in the absence of life that are beyond this 15 steps. So this idea of this complexity threshold, this space is exponentially growing as you're building up more and more complex molecules. There's an exponentially growing size of this space. The only process that actually can allow you to observe objects in high abundance above that space, we conjecture, is an evolutionary process, or one that has selection and information processing system in it. And so this has been empirically validated with this work as far as how we think about it in terms of these assembly steps. So that's sort of giving a broad view of sort of the theoretical foundations, and then also how we can measure this property with standard instrumentation. The orbit trap that they used for the mass spec work obviously can't fly on a mission to Mars to actually detect complex molecules, but we're working on the resolution of mass spec instrumentation to measure this property of complexity in molecules and determine if we can actually use it in planetary missions to look for complexity as a signature of life. The last part I want to talk about is whether we can use this as a sort of means to think about origin of life experiments, and also how they might relate to thinking about life as a planetary process, what kind of geochemistries can give rise to life, and then also what is the potentiality for life in a Martian environment, at least an origin of life event. And so this is kind of switching gears a bit, but this work is deeply related to the theoretical work we're doing. My colleague Lee Crone at University of Glasgow, who I'm developing the theory with, also has a whole bunch of origin of life chemistry experiments running in his lab on a platform called the Computer, which is an automated system that basically has allows exploration of a lot of chemical space, because you're basically now doing all of chemical synthesis with robots, and it's programmable. And so the idea we have in mind is that we might be able to build a large enough origin of life engine that can explore enough different geochemical environments to actually see the spontaneous emergence of evolution and selection, and that we can use this assembly theory as a way to measure that process happening in a chemical system. And so I'm kind of interested in actually taking known geochemistry from different planetary environments. So for example, we visited a lot of sites on Mars, and can we actually use some of these conditions that we know of on these other planets to actually look for how we might induce life? How could we actually have de novo alien life emerge on Mars if we can't discover it there? I think the origin of life is actually the same problem as alien life detection, in the sense that if we can solve the origin of life, we've basically made alien chemistry in the lab. So I'm going to stop there just in the interest of time. I want to thank all of you for listening, and also my lab is amazing. And I hope there's time for questions, but if not, I'll be around for a little bit. So thanks.
I think we have time for one question.
Sure. Great.
So you talk about measuring the complexity of molecules based on the number of new bonds and new structures that get added to them.
Yes.
How does the theory account for potential repeated structures added to things like a polymer chain?
It's naturally recursive. So it's not just the number of steps, it's the number of steps where you actually look at reusing parts. So recounting structures is actually already embedded in that assembly index. So if you have a very large molecule, the most interesting ones are actually going to be asymmetric.
Yeah. Okay. That makes sense.
And not reuse parts, because they tend to have lower assembly index if they reuse parts.
Got it.
Thank you so much. Oh, we'll go ahead and take him.
Sure. Mm-hmm.
Back in 2012 at Berkeley, we built a Mars chamber, reproducing the Mars environment as closely, with the exception of gravity. And into that chamber, we put halophile bacteria.
Oh, that's cool.
And we watched them and watched what happened. And about 2 months later, the original population had gone down from 100% to about 30%, but it had stabilized. And then we stopped the experiment. So the question to you is, had we continued that experiment indefinitely, would that population have evolved to what you're thinking about? And would you be able to study that evolution in an experiment like that? I don't think anybody's done an experiment like that, but that's the question.
Yeah, I think I'd have to dig into the details of your specific experiment to answer that more directly, but I think in general, we are very interested in using this as a paradigm for studying experimental evolution, both in terms of chemical systems that are not alive yet and how you can actually make them transition, but also in living systems, you know, can you predict trajectories of evolution? And I think there's some features of this kind of framing that actually allow us to predict what kinds of molecules are likely to actually appear in evolution based on the structures that exist now. So it'd be interesting to test in a case study like that. And also try maybe test hypotheses about things that are geochemically compatible with Mars, which I'm very interested in. Thanks.
Thank you, Dr. Warren.
Thank you.
Thank you. Look at that. All right. Next up, we have Dr. Greg Autry, who is the Director of Space Leadership, Policy, and Business at ASU's Thunderbird School of Global Management. He is a visiting professor at Imperial College London and Vice President of the National Space Society. Autry served as White House liaison at NASA and was nominated by the president to be the NASA CFO. He also chaired the Safety Working Group on the FAA's Commercial Space Transportation Agency Committee. His books include Death by China and A New Entrepreneurial Dynamic. He regularly publishes in Foreign Policy, Forbes, and Space News. Welcome, Dr. Greg Autry.
Thank you.
Thank you. I'm glad you noticed them. We were just noting, I've got a really cool Psyche pen that I want to thank Nikki Fox, who's the head of NASA Science Mission Directorate, for giving me, and I decided to put Psyche up on my opening slide. How many will be trying to go out and see the Psyche launch next Thursday? Anyone? Strongly recommended. There is nothing cooler than a Falcon Heavy launch and booster return. I've had the privilege to see that, and I can't wait to see it again. It's also really cool to see a commercial rocket launching a science mission, and to see that we now have options on different rockets to launch deep space science missions. That's going to be exciting. I want to talk about something that's been bothering me, and something I've been writing and speaking in other forums about. And that is this. Now, when I say we are not alone, I'm not talking about the biology we were just covering. I'm talking about this. You might have noticed the Russians tried to put a lander on the moon and they failed. I think that might be the RIP for the Russian space program. I think Mr. Putin and his henchmen like Dmitry Rogozin have killed that once glorious and noble beast. The Indians did land on the moon, did they not? Japan, a private company, tried to do that. I'm still very impressed at their effort. I think they'll do it on the second try. The Israelis tried it a few years ago. I think they'll be coming back. I have to say, extremely shocked and horrified at what we've seen happening in Israel the last few days. But I do wish them the best and hope their private space program gets back on track. The Chinese, of course, have done this, right? So we see science coming from a lot of different sources that we didn't see before, different nations and even commercial companies and private organizations in different countries. This should excite us and create opportunities for NASA to engage in a lot of ways, but it should also motivate us to realize that we want to stay number one, that NASA should be the world's top space science organization, and we want to stay there. So what are we doing about this? Apparently, Congress, who was dysfunctional even before last week, has decided to trim the NASA science budget. Okay, this is baffling in so many ways, and I'm going to get into to why that is. But we've all going to have to work together to address this issue, because it's important for what you want to do in the Mars Society and what we all want to do in the future of humanity. One of the examples that really stood out was the the pressure on SMD to cut budgets meant that you had to redeploy or perhaps semi-retire programs that were already out there in deep space, things we'd already spent an awful lot of money on developing and deploying, including most notably the New Horizons probe that Alan Stern flew by Pluto, and the really cool flyby of a Kuiper Belt object is still out there in what appears to be a larger Kuiper Belt than we thought. And there could be an opportunity for another Kuiper Belt object observation. We don't know. They're looking hard for objects, but while we're out there, we'd like to be able to do that. And we were on the verge of that not happening, that big sunk cost investment we'd already made would have had to been redeployed because of Congress chopping the budget. The Mars Sample Return Program, which might answer that question we have about life on Mars, or at least give us a lot more data on what we need to know about developing life and maintaining life on Mars in the future, is in danger of getting axed. I think we're going to have to look at this, and those of you familiar with the story of the better, faster, cheaper model, we learned that you can only do 2 of those things, right? And I suspect in order to operate in the political and budgetary climate we have, we're going to have to do faster and cheaper and do better later. In my opinion, we want to get that sample back in a reasonable amount of time before Elon shows up with a bunch of people and makes it pointless, right? But I think you get that sample back and you show that chemistry, and I suspect you're going to find out that there was life on Mars at one point, if there not is life on Mars. But if you find that, it's going to be a lot easier to get the rest of the budget. So I'm all about faster on this. And I know there are people here at ASU that are deeply involved. If you look at the NASA budget overall, this information is available to you, the public, online at NASA's website. If anybody doesn't know where to find it, I'd be glad to help you do that. I will say sometimes it's presented in ways that it's very hard to ferret out the total cost of a single artifact in the system. Like if you want to know what a particular rocket costs to build and operate, it's spread out among these different budgets. But the top line budget up here has generally been going up for the last few years. I'm proud that the previous administration kicked it up a little bit, and really pleased that the Biden administration has continued to make requests that provide significant increases for NASA overall. But it's about 6%. That doesn't even keep up with inflation, which is now driving at about 6% annually for the last couple of years. Maybe it's going down, maybe it's going to go back up, but we are in an inflationary environment. This is not a big increase. If you look down in the sciences budget and you compare the planetary sciences budget, which is the second line to the earth sciences budget, and you look at these increases, the increase for planetary over the next several years is going to bump it up maybe 5 or 6% over several years, not 5 or 6% per year. So it's actually going down in what we economists call real numbers. We're actually losing money because inflation is running higher than the increases. The earth sciences, on the other hand, is getting almost a 40% kick up over this period of time because the current administration has a strong interest there. But we need to fight more on the planetary sciences side, right? And push for the argument of why that's important. And one of the arguments I would make to people who love the earth sciences is we can understand a lot more about the earth when we understand a lot more about Mars and Venus in particular. What happened there, right? Why were they climactic disasters in 2 different directions? If we understand that, we'll know a lot more about what we need to do with the Earth. This is near and dear to my heart, commercial LEO development. These are the commercial stations that will replace the International Space Station. And I serve on a committee for NASA out of JSC called NSPA, the N-Space Production Applications Program. And I help vet the business plan for missions that NASA funds and provides up mass and down mass and some astronaut time for to do manufacturing tests on ISS. But the goal is to develop an in-space economy that actually delivers some value back to Earth. And there are some amazing things. Please go to the NSPA website if you're not familiar with it. But everything from amazing new materials, crystals, artificial retinas and artificial organs and stem cell developments that may truly transform our lives in just the next few years are happening in microgravity. Doing that on CLDs would be great. In my opinion, this is the best value line item in the whole NASA budget. This is so inexpensive because it's leveraging an awful lot of real private capital that's going into these programs from companies like Axiom, from the participants in the Orbital Reef Project, the Blue Origin, Sierra Nevada tie-up, and the Starlab group from Lockheed and from NanoRacks and others. This is disappointing. You're not getting to Mars this way. This is never going to happen. And I've said before, I don't believe the United States Congress has the cojones to fund an actual Mars human mission. I don't think that it'll ever happen as a purely governmental program like you saw in The Martian. We're going to have to rely on the private sector to step in and make that happen. But don't believe that it's happening there. The Artemis campaign, now you're getting double over this period of time on that budget. And you might think, if I'm all about Mars, that I don't like that this money should be redirected to Mars. But let me point out that one of the things you're getting out of that is this, which is probably the best thing that you have going to get to Mars. By funding Starship as an HLS system, you are really, really paving the way for Mars. So in my opinion, that's where the Mars value has been going, not in the line item that actually says Mars. Now let's look at this. This is very disappointing. This is the NASA budget is a percentage of all federal spending, right? So I'm not just correcting for inflation, I'm correcting for the fact that whether you like it or not, we live in a world where the federal government grows and grows and grows faster than the economy every year, and it becomes a bigger and bigger portion of our economy. And the NASA budget is not at all keeping up with that. And then I wonder, why would NASA be a budget target for Congress? They're going to save your money, right? Now, I'm all about that. I do think that the federal budget has been growing out of control, particularly in the last few years, and some parsimony is definitely called for. And I respect people in Congress that have stepped up on that. But going after the NASA budget, let me show you something. There's two lines here. The blue line is federal spending, and the dotted line is federal spending with the entire NASA budget removed. If we close down headquarters and all the centers, and your friend said that money that you people are wasting on space was sent back, that's what you'd have, right? You can't see it. It's irrelevant. And that's the entire NASA budget. I'm not just talking about the little part that's the science budget, which was completely irrelevant. Congress is simply showing that they're willing to cut everything. And unfortunately, what they're cutting is your future. So where is the money all going then as that federal budget grows? There are two line items here. Both of them really got started in the 1960s. One is NASA and one is Medicare. Medicare is the red line and NASA is the blue line. Medicare is well on its way to $1 trillion a year, right? And have any of you seen those stickers that say Medicare for all? Well, this is not the best managed program that's ever been. If you like the idea of universal health care and feel that that's a human right, that's great. But trust me, Medicare for all means nothing else will ever happen in this country except Medicare. NASA will close down, along with a lot of other programs you love. It is not a solution to healthcare. Can you? Yes, I'm not kidding. That's the truth. Medicare eats the annual NASA budget every week. When you think about New Horizons, luckily, NASA was able to work something out, trimming the budget on New Horizons, but continuing both its mission for helioscience and keeping an eye out for Kuiper Belt objects while it's still in the Kuiper Belt. But that took a whole lot of work. Did any of you sign on to the change.org petition on that the National Space Society put forward? Yeah. And I and a handful of people few months before that had sent a private letter and signed on to it, encouraging that we continue New Horizons. And I will say the space community, I think, made a difference here, but it was a $10 million fight. Okay, that's what it cost, $10 million a year to keep New Horizons going. Medicare spends $100 million an hour. Okay. Yeah, some of us are doing that, right? And someday I'm going to be consuming that money too. But we do need to think about whether our priorities are they in the future or are they in the past? I'll get to questions. I'll get to questions at the end. Thank you. And that was one of the things I wanted to mention. So the F-35 is another great example that I often cite. The budget overrun on the F-35 is $180 billion. Okay, it is multiple sizes over the NASA budget, and that's just the cost overruns. That's not the planes themselves. That's the cost overruns. Medicare again. The government admits, this is a government website, the second page, that $60 billion a year is being stolen from Medicare. Okay, so basically more than twice the entire NASA budget is money the government admits that they're having stolen from the Medicare budget. So the point I'm making isn't so much to bash on Medicare, although I'm certainly not a fan of the way it's managed. But the point I'm making is that if anybody says to you that we're spending too much money on space or cutting the NASA budget is going to do a lick of good in the federal government, they are completely misinformed, and you need to correct them on this. All right. And you do. You need to make sure everybody understands this, because there's this general perception that going to space is incredibly costly and is a great expense to the US taxpayer that maybe we can't afford because we have real problems here on Earth. What can you do about this? Well, first of all, I want you to tell the story to all sides in the political battle here, okay? So two of the techniques I like to use is talk about how space can protect our planet. As I mentioned, understanding what happened to Venus and understanding what happened to Mars will allow us to better understand our own climate. And of course, we develop a lot of sensors and technology to explore those planets that we can point right back here on Earth and do. And that appeals to people who are very concerned, particularly on the progressive side, about climate change and other environmental disasters that are befalling us. On the hawkish right side, talk to them about that competition with China and the fact that we're not keeping up in that race. And find out what the trigger is for the person that you're talking to and explain to them why space is relevant to them. And we need all of you out there doing that. I want you to go to the Hill. I want you to go visit with your congressperson. You can do it in your district, or if you're in DC, do it there. Request a meeting and try to talk to your congressperson, or at least their chief of staff and policy team. They owe you that meeting if you're one of their constituents. And if you're a subject matter expert on something in space, you can often get meetings with people who aren't even your congressman. I started doing this on my own, at my own cost. More than 15 years ago. I just started going to DC and walking the halls and talking to them in particular about the power of commercial space and why I felt that was important. And I got traction, and I've actually been able to influence some decisions there because I made a great network of friends. You should all be doing that. Now, you can also do that in concert with organizations like the Mars Society. So by supporting the Mars Society, Bob and James, they're talking to these people, and they get calls from people on the Hill that ask their opinion. So keep being a supporter of the Mars Society. The Planetary Society runs a very, very good lobbying program in DC in support of space science. I would encourage you, if you have the funds, to be a member of both groups, because I think we need robots and humans, and they should be working together. The Planetary Society, National Space Society also run March Storm events where they ask their members to come out and go to DC in a group and go talk to members of Congress, and you can do that. But again, talk to your friends. Now, another thing I'd like to do, frankly, is a little bit of change at NASA. We've got a certain amount of money. I don't think it's going to get hugely larger, even though if I had the choice, I would invest much more money in our future than in our past, meaning into NASA, into education, into science and engineering broadly, as opposed to funding the last generation. But part of this is organizational. When you go to NASA, has anybody ever been down this hallway? I'm sure you have, Bob. I call this the hallway of intimidation. Okay. To go see the NASA administrator or this group of hallowed people in the administrative suite where, I don't know, there's probably 30 or 40 people in this isolated suite. You have to walk down this narrow hallway with the oil paintings of all the and deputies on the other. And some of these are people I love and admire, but can you imagine if you were a 24-year-old engineer with a brilliant idea on how you could help NASA save money, right? And you want to see the administrator. First of all, by the time you get to the end of that hallway, you feel like you're about this big, right? And then you get to the door, and the door basically says you don't belong here, right? And there's a little sign you can't quite read on the left there that says you have to go talk to the receptionist. So you got to go see a receptionist just to get into this part of the building on the 9th floor in DC. And then there's another receptionist to stop you from getting to the administrator, right? It's all very nicely appointed. This was the waiting room outside my office when I was the White House liaison. And this was my office, which was kind of cool. Right before I moved in, actually, I hadn't hung the artwork up on the floor down there, but somebody gave me an Antares rocket model just to poke at me, I think, because they knew I had this commercial bent. But I want to contrast this, okay, to Elon Musk's cubicle, okay? This photo I took with Elon in his cubicle at SpaceX. And if you look at the background there, you can see he is accessible to anybody in the organization. Now, you better have a darn good reason to go interrupt Elon Musk with something. But if you need to talk to Elon, you can get to him. If you work at NASA and want to talk to the NASA administrator, good friggin' luck getting that done, right? There's no bumping into him at the water cooler or the bathroom because they have their own water cooler in their own bathrooms. They got their own patio up there and they're isolated. This is a bad plan for running an organization. In my plan, everybody should be sitting in a bullpen sort of operation to be accessible to everybody and working like a team on the ground. All right, those are the things that I don't like. Are there good things? Yes, there are. Okay. So from a US perspective, look at that. Orbital launches by country, basically almost half of them in 2023 to date have been American. And I believe by next year, 3/4 of orbital launches will be American. Orbital launches by vehicle, this is really important. Most of them are Falcon 9, a vehicle that is primarily commercially developed with a few $100 million in well-invested NASA money. This points, I think, to the value of NASA money invested along with larger amounts of private capital. And I hope that the commercial LEO destinations will do the same thing. This is the way we need to get to Mars. The same plan where NASA puts in seed money for technologies that are going to work and requires significant private investment. If private investment doesn't show up, you pull the plug, which they did in the COTS program, which funded Falcon 9. They rejected companies that couldn't secure private funding. Satellites. We've got a lot of satellites up there. Why do I care from a science perspective? Well, I care from a science perspective because every one of those satellites is lowering the cost of science missions in the future by commoditizing the entire satellite supply chain of components. And just think, if we've got 40,000 Starlink satellites up there or 5,000 Kuiper satellites up there, could we make a deal with those companies to put a couple extra sensors on a platform that is already in orbit, has great power, has great communications, and collect some science data about our atmosphere, whatever we want to? Yeah, we probably could. And we're going to find that the ability to mass produce satellites in these quantities is going to transform science. Now, this came from Statistica, and I want to also point out a couple of things. There is no Commonwealth of Independent States, and China is not a people's republic, and we shouldn't say things that are not true. All right. Most of these satellites, again, are commercial US satellites being built on an incredibly new, efficient production line that Musk and his team have put together, and this will change the world very much the way that Falcon 9 did. And we've got an incredible livery of new rockets, spacecraft, and these commercial LEO destinations coming out. We're going to be able to do so much science there, and much of it will pave the way for us to get to Mars. We are in a good place. Now, I get the question, shouldn't we all work together, right? Well, this kumbaya thing comes along a lot, but I want to point this out. I like to say conflict is bad. I don't think anybody rational disagrees with that, but competition is really, really good. I am so happy that China is doing a fantastic job with their space program. They're kind of slow, but they're methodical and they deliver when they say they're gonna, and there's good competition. If you look at Sputnik in 1957, it freaked out everybody in the United States, but 13 years later, we had this, and we had this primarily because it freaked out everybody in the United States, and people did what I'm doing now and said, hey, members of Congress, hey, White House, you need to go out and fund space because it's a competitive matter that matters. 13 years, look at that, to technology that was just a basketball that went beep, beep, beep. It did no science. It had no real mission other than to show that we could put something over your head. 13 years later, we have something that still oddly, these images still kind of define modernity today. Then in 1974, we had the handshake in space with Apollo Soyuz, and we started working together, and everybody says, imagine what we'll accomplish now that we're working with the Russians. Not very much. 25 years later, we were in the same orbital inclination at 51 degrees and the same altitude at 250, and we still had a Soyuz plugged onto the end of that thing. 22 years later, we've got a bigger version of the same thing in the exact same place. We haven't gone anywhere near, and there's still a Soyuz plugged onto the thing, right? So cooperation is dull. Nobody wants to go to an Olympic game where the goal is to have all the nations cross the line at the same time, holding hands and singing, right? We want competition. It's a beautiful thing. All right, real shameless plug for another event, and I'll take questions if there's time. I'm hosting the 2023 National Space Society Space Settlement Summit here in Phoenix, October 27th and 28th. It's in downtown at Thunderbird's global headquarters. And that's a fantastic building. It's way better than this building. You should be there. And I think you've heard about Thunderbird. Here's just an interior shot of our building here in Phoenix and our building in LA, the ASU building. And some of our students out in the field, we are changing the world, and we'd love to have you. So do I have time for a couple questions?
Absolutely.
Thanks. No, I set a timer and I beat it. I have 4.5 minutes.
Sorry,
Every speaker should set a timer.
yeah, thanks for the excellent presentation. Actually, I wrote a very lengthy question for you, but you answered that question about the competition and collaboration in your last segment.
Okay.
But what I still think that, I mean, competition can take us to low Earth orbit, to moon, but for Mars, I still think that we still need a global collaboration that will take us to Mars and beyond. But that's just my thought. What are your thoughts about that?
Okay. I would love to see a global, what I call co-opetition going to Mars, meaning people trying to beat each other to do it better with multiple ways. If we all got together and did a UN space program, we will never get to Mars. I swear to that. Okay. That's just not going to happen. I love the vision and idea of the UN, but don't fall in love with an idea if it doesn't actually deliver. Okay. Because when it comes to actually delivering, they deliver speeches and paperwork. If you want to actually make it happen, I think it's going to fall in the commercial industries because the United States government can't afford to fund it. China is having an iffy moment right now, but maybe they'll get it together and resume their growth track. And if they could do it, but I don't think so. Their demographics don't play it up. I'm really excited about what India is doing. ISRO, amazing example of what a government space agency can do efficiently. I'd like to see them there, but still in the end, I think it's going to be Elon and in relativity space and some other folks that are going to focus on how do we do that, right?
Hey, Greg, excellent presentation. Very awesome. I was wondering, something I thought about while you're doing the presentation is I just realized that SpaceX uses its launches and the revenue from Starlink to fund the development of Starship. So has it crossed the minds of anyone at NASA? Maybe they've thought about this, but to do something like asteroid mining as a lucrative way to fund their missions so they don't have to go hat in hand to Congress? Is that ever?
Yeah, if you've watched like For All Mankind, NASA seems to quasi be in some sort of business. In my opinion, having worked at NASA and having spent time inside the federal government, no, you'd end up with the post office. Post office, in case you're wondering, is never made money. At one time, it was a very necessary service that I think made sense from an infrastructure standpoint. Today, in fact, I wrote an editorial questioning whether the post office is just a way to deliver trash to my mailbox that other government. other government tracks pick up. But anyway, I don't think NASA should do that. I do think, though, that NASA always needs to be looking at these opportunities, and they are. And they're really smart about this with CLDs, with the NSPA program, with COTS and commercial crew, opportunities to put in the seed funding so that private organizations that are more efficient than the federal government can step in and make it happen. So yeah, whether that's asteroid mining or anything else, that's the model that I think gets us to Mars.
So one last question.
Okay.
You riffing on what you just said and considering all the detailed information that you had about rocket launchers and things. I noticed that you didn't mention Rocket Lab's Neutron as one of the heavy lift vehicles.
Yeah, no, I wish I could put Firefly there, Neutron. It wasn't a lack of respect. I love what Rocket Lab's been doing, and they're actually flying. I think Neutron is a really neat design, and one that may be more practical perhaps than Starship. And I love to see that competition. I really want to see Peter and Elon at each other, because they'll both be so much better when we're there. So yeah, kudos to Rocket Lab, again, Firefly, a lot of other great companies. Relativity Space started by two students I mentored at USC. I can't say enough about all those companies. We are in a golden moment. I just don't want Congress to quash this golden moment.
And actually, Relativity is our next speaker.
Great. Well, then I will look forward to it. Thank you,
so much,
James.
Greg. Grab your microphone. Thank you very much. So as I just mentioned, our next speaker is Tim Ellis from Relativity. Now, he was not able to make it in person, and he was also not able to do a virtual talk today, but he did pre-record a talk. And so I'm about to play that. And Dr. Autry and I talked earlier today, and for the Q&A portion, Dr. Autry will take a stab at answering questions. Obviously, he's not going to be able to speak to everything that they're doing, but he was an advisor to Tim Ellis. And so he does know a little bit about what they're doing. So with that, I will go ahead and start the pre-recorded talk.
Hello, everyone. I'm excited to see you go very news with us.
Hold on one second. I apologize. I want to make sure the Zoom is hearing that as well. I got this tricky little checkbox that you got to check. If you don't do that, they won't hear it. All right, let's try that again.
Our society virtually. Excited to talk about relativity and one of my favorite topics, Mars. So going back to when I started Relativity in 2016 at the very beginning of the year, really kind of part of the history of why I decided to leave Blue Origin, where I was a propulsion engineer. I had started the metal 3D printing division, and that was off to a good start. I was really candidly stepping back and looking at the rest of the commercial space industry. So I was seeing SpaceX land rockets, dock with the International Space Station. At the time, even at the end of 2015, they had just landed successfully their first rocket out in the ocean. It was a very exciting time. But despite that, they were a 13-year-old company, and they were still the only company in the world that had this core mission of making humanity multiplanetary and the long-term goal of sending 1 million people to live sustainably on Mars. So I really thought that that was actually quite depressing, that despite 13 years of once-in-a-generation success, they had really had not inspired a second company to be founded. And I really felt, looking at this goal from a practical lens, 1 million people on Mars is a crazy ambitious achievement. And so it was obvious there had to be more like a dozen to 100 companies working on this successfully with other government agencies and entities to make that mission possible, even remotely close in our lifetime. And so I started Relativity with the goal of being that second private space company working to put 1 million people on Mars. I really think that 3D printing technology is inevitably required to build an industrial base on Mars. So initially, I really looked at this problem as saying, well, what is the inevitable factory that must exist on another planet? It was clear it needed to be small and lightweight. It needed to be able to then fit and launch on a rocket to Mars. It needed to build a wide range of products with very little human labor, human involvement, given the scarcity of labor once we do have humans on Mars. And then it also needed to be quite intelligent and be able to react to very uncertain conditions that we would not perfectly be able to test on Earth and would be so far away that it needed to be very adaptable. So all of those North Star parameters really for me started to describe an intelligent 3D printing system, likely one that will use AI and other advanced software and data technologies as we mature them. But really 3D printing is the backbone of what I believe will build humanity's industrial base on Mars. And so I thought we could be the ones to do that. Somebody has to start this company if that future will exist. And so that might as well be us. So at 25, right out of Blue Origin, started Relativity Space. Initially, our first chapter as a company was Terran 1. So I really viewed our trajectory as 4 main chapters. So starting with chapter 1, which we just completed, which was proving the viability of the world's largest scale metal 3D printing technology, as well as our methane propulsion technologies, et cetera. So with Terran 1, which we just successfully launched to space in our first launch, I think by many measures, it was one of, if not the most successful privately backed company's first launch ever. So we proved our 3D printing technology worked for an 85% 3D printed rocket. We proved our liquid oxygen, liquid methane propulsion technologies really got all the way to space, which way exceeded our goal of getting through max Q, or the max stress on our rocket. And so that gave us enough confidence where then the first thing I did was went and called our customers, asked them to tell us, how do you think we did? Was that enough of a proof point and enough of a success to go and move on to Terran R, which had already been in development at that point for about 2 to 2.5 years. And then everybody unanimously said yes, that they thought that was successful enough. Getting the second stage engine to light, we collected enough data that we know what happened and we know how to fix that particular issue. We just want to fix it on the problem and the product that really pushes humanity forward and solves the biggest customer need, which is very clearly now, kind of 8 years after founding Relativity, that there's still not a second great commercial launch company. Really, there of course is Rocket Lab. They've had a lot of successful launches of a small CubeSat rocket. There's other kind of semi-private national entities like ULA and Arianespace globally. There's other large rocket companies in development like Blue Origin. And then, of course, SpaceX, which I'm still remain a very big fan of. And it doesn't take me to validate. They've had a monster year this year with both Falcon 9. I think Starship progress and development is progressing. And I certainly believe eventually Starship certainly will work. I'm counting on it to work because we need it to launch humanity to Mars. I think it's a big piece of making that future happen. So definitely rooting it on. But it's clear on a commercial side that there's still not really an obvious second player that's just as quickly moving, low cost, and has a very capable launch vehicle in the heavy lift payload class. And so that's really where we see Terran R, which is our chapter 2 at Relativity, now fitting. So we're 100% focused on Terran R. Of our 1,000-person team or so we have now, everybody is working on Terran R and 3D printing technology that supports Terran R. So this is really our chapter 2, is to build the next great launch company. And then chapter 3, which I'll go into kind of briefly, is really then using this 3D printing capability. Once we've proven we can build a highly reusable rocket, initially Terran R is developed for 20 reuses. But I certainly think we can push that much further. We're actually actively developing a third generation 3D printed metal alloy, which would allow us to reuse beyond 20 reuses. We're working on thermal protection systems and other design architecture improvements that would allow us to have more than 20 reuses per Terran R vehicle built. That those kind of technologies will also then really mature the 3D printing platform. And I think at its core, then we can build in chapter 3 to be the world's next great aerospace company. So really using the same kind of highly iterative less fixed tooling, more automated production process that 3D printing really enables. As that technology continues to mature, I think other products will be able to be disrupted using this core tech. So I actually see our kind of roadmap looking more like a Tesla over time, in the sense that we have this core tech. Terran 1 was like our Roadster, Terran R is like the Model S, and then we'll have other additional products on top of that. So certainly there are other things in space that could potentially be on that roadmap. I think looking at what kind of industrialized products will also be useful for Mars, and how can we get a leg up on creating some of those technologies that are both killer businesses on Earth, but also add up to helping make this future happen on Mars, then really leads us to chapter 4. So chapter 4 is building the industrial base on Mars. This has really been a core part of Relativity's vision and strategy literally since the beginning. I have a Starbucks receipt that we actually drew out basically those 4 chapters, and how 3D printing will help get us to Mars, and how that really is an enabling technology for making this happen. So that's really the high level strategy. It has not changed much for the last 8 years. There was actually periods in time where we really thought we wanted to do the Terran R rocket first and get there as quickly as we possibly could. But it's a 3.3 million pound thrust, 23.5 ton to LEO payload, reusable launch vehicle. So this is a definitely heavy lift launch vehicle at this point, and jumping straight to that would have been a huge leap. But as far as where we're at on that journey of developing Terran R, so as I mentioned, we're over 3 years into the development. We're going to complete a preliminary design review of the entire vehicle towards the end of this year, beginning of next year. So at that level, almost every detailed part will have been designed. We have a full 3D CAD model of the rocket, and we have a ton of hardware that we're producing too. So we just hit our 500th engine program test milestone. So this is a 258,000 pound thrust, liquid oxygen, liquid methane, gas generator rocket engine. So fully designed and developed in-house. This particular engine really has a lot of the same design architecture of Aeon 1, which was the first engine that we flew. So that is helping us accelerate the development of this launch vehicle program. As we have the same propellants. We had already collected well over 10,000 seconds of engine testing on Aeon 1 before it flew. We had produced dozens of engines at the time of first launch. And then, so we're really using that same 3D printing approach, plus really pushing the 3D printing tech even further with new materials. We have a hybrid multi 3D printer approach to building Aeon R, since it's a much larger engine. But we've already produced now over a dozen chambers. We've actually tested all of the major components at 100% power, from the thrust chamber assembly to all of the in-house designed valves, both turbo pumps, the gas generator, etc. So really there's already quite a bit of momentum towards this. From Terran R's perspective, we're on track for first launch in 2026. I'm very excited for it because we also have an exclusive contract and partnership with Tom Mueller's company Impulse Space to launch the first commercially funded mission to Mars. So this is a kind of JPL style reentry aero capsule. Tom and the Impulse team are developing the transfer vehicle as well as the lander and the reentry capsule for Mars. But we're focused on building the launch vehicle, which is really just Terran R, what we already have to develop and build. But we have exclusivity through the next 2 Mars launch windows, so Q4 2026, as well as the window at the end of 2028, very beginning of 2029. And so we have 2 shots on goal to hit this timeline and to launch this mission. So I'm excited about it because they're really, certainly, as I mentioned before, I believe in Starship. I think what they're doing is fantastic, and having very heavy lift payloads with refueling in orbit in order to launch payloads to Mars. What we're developing is a little bit more akin to what JPL has done So really standing on a lot of the work that JPL and NASA had done to date. And we're leveraging that work to have a more traditional looking mission, but one that can send small, useful science payloads to Mars's surface. I think initially we have not officially talked about what payload we're going to send, but I can almost be certain that we're going to push quite hard for it to be a 3D printed, related subsystem or something to really show this idea of building an industrial base on Mars and taking the first step towards doing that. So I think initially with 3D printing and with some of these missions, we just want to prove out the base initial technology. So I think initially things that we will send to Mars will likely have to come with materials sent from Earth. So any 3D printers will be more of a mission enhancement that can really build things like spare parts that may break or need replaced or refurbishment once you're actually there. Even if you're bringing the materials initially, it gives you the flexibility to build way more replacement pieces to really increase the reliability and robustness of a mission. I think that will eventually expand to other lightweight, kind of high volume pressure vessels and other similar objects. So those are some of the worst things to launch on a rocket because they're very physically large, but they take up a lot of launch volume, but they do not weigh very much. And so I think even if you're initially sending the materials there before doing in situ resource utilization, this really still will provide a pretty big mission impact and kind of provide those very early seeds and ability to actually build things on another planet. So I definitely want to talk a bit here about why Mars. Of course, this is absolutely the audience to do it. So I think for me, taking a step back, I think this idea of an asteroid destroying Earth and kind of a backup for human civilization due to that is quite unlikely. I think it's much more likely in the next 100 to 200 years that we destroy ourselves than an asteroid destroys us. So, I think that particular argument, it's more likely we're going to cause our own self-destruction than that. But for me, I really do agree with this idea of expanding human consciousness. But I think for me, I really take it from this standpoint of we've lived on Earth for thousands and thousands and thousands of years as a modern society. We have improved generation to generation, step by step. And I think we live at a time period where we get to ask ourselves, what is that all for? Like, what is the North Star trajectory of human civilization and humanity as a species? I think due to social media and fragmentation of the news and information, as much information as there is available, I think there's a lot of fragmentation in modern society. And so we need another unified North Star to really go after again as a society and as a species. And I think personally, this idea of 1 million people living on another planet and going after that goal is fundamentally expanding the experience of what it means to be a human being. So I really believe in this idea of expanding the possibilities for emotional kind of insight, for self-reflection, for government, for art, for really just expanding the possibilities of human experience. I think for me, that is the reason to go to Mars. It does not purely have to be economic or scientific. Certainly, there will be an expansion of the economy. There's lots of practical benefits, but I think for me, what gets me up out of bed and excited to go build Relativity together with our dedicated, passionate team every day is this idea that we as a industry and a commercial space and government space industry can come together and can be part of developing humanity from a single cell organism to a multi-cell organism, not just for survival, but for answering these existential questions of what does it mean to be a human? What is the human experience? And how do we expand what humans can experience more and more in the physical and the real world, where it's exploration and not just imploration in VR and AR and going inside ourselves, which technology has done a fantastic job expanding the boundaries of that. But I really am worried that if inflammation and VR and AR technologies get so good that we will eventually potentially lose our drive to explore, because exploring is so much harder. So I think that the last point I'll leave as far as why now and why this is important to tackle at this point in time. So I certainly think AI will be a huge breakthrough in making this happen. I think when you look at what makes human spaceflight difficult, really the human body is one of the biggest things. So food, water, shelter, boredom are the four things that make human spaceflight fundamentally difficult, or more difficult than just sending robots and probes. And so I think because of the trajectory of AI and robotics, I don't know if it's the next 50 years, the next 100 years, the next 150 years, but there's going to quickly come an inflection point where the incentive to send human beings in our squishy, fragile bodies is so much lower than how good AI and robotics will get at some point in the future, that the incentive to send people will just begin to decrease. It will be so much better to send whatever very advanced versions of, maybe self-organizing swarm robotics, like other kind of technologies that will develop and will mature. That I think we really live in the golden era and the golden window of only a couple decades to 100 or less years, that this is really the right time to send people in mass and at scale for just the pure reason of humans experiencing this ourselves. So really, I think that's why now, and that's why I certainly feel a lot of urgency around it. And I still very much believe we can all come together and make that mission happen with the right focus and the right dedication, and inspiring more companies to join in this mission of going to Mars. So with that, hope you have a great rest of your conference, and I was excited to share an update with all of you. See you. Hello, everyone. Excited to join you and the rest of the Mars Society virtually.
Okay, and let me clearly say, I worked with Tim and Jordan when they were students at University of Southern California, where I taught for many years. And I've got a nice interview with Tim in my book, The New Entrepreneurial Dynamic, if you ever feel compelled to read a entrepreneurship textbook. But I don't have any formal relationship with them at this point, and I'm in no way answering questions on their behalf. I'll answer questions about them based on my information, but I was a formal advisor at one time. I am not at this moment. Yes.
Hey, Greg. I gotta admit.
Tim says hi, by the way.
Hi, Tim. I gotta admit, I'm actually kind of jealous because I think they've hit like engineering gold mine right over here. Because I think this is like, as Bob said, like selling the jeans and the pickaxes to the asteroid miners of the future. Because this is something that, like as you said, competitively, I think would make SpaceX feel a little uncomfortable, because manufacturing and machining is really hard. And 3D printing could really move things along really fast. So I was just kind of curious, are they thinking about like a product roadmap in terms of like 3D printing spacesuits, HAB modules, lessons learned from the rocket, you think?
Yeah, well, it's interesting. When Jordan and Tim were both at Blue and SpaceX respectively, they would talk to me about how these companies weren't taking advantage of 3D printing enough. They were using 3D printing to do some things like internal structures in engines with turboprops and stuff that couldn't be machined easily, or if you machined them, you then had to bolt them together, and there was a lot of labor and a lot of failure points. And so they would only do 3D printing where it wasn't easy to do otherwise, right? And beyond that, no. And Tim, you started up the 3D printing at Blue, and then tried to get them to do more of it, and they wouldn't. Since then, though, he's learned that everything can't be 3D printed, and if you're paying attention to the news, you're going to see they're going to dial back their 3D printed content on their next rocket a little bit, because there's some things where it doesn't really add value. and a lot of people questioned, why would you make a pressure vessel or, the fuselage, a tube of a rocket when, you can just roll that and stir weld it. There are times when you add value, times when you don't. They're going to look at that. Spacesuits, gee, I don't know, but I bet a lot of components on spacesuits for sure should be 3D printed and can. And one of the great things about 3D printing, it's not just an issue of how much labor is involved or cost. It's the ability to make a design change quickly, right? So if Relativity wanted to change the shape of their fairing slightly, right? Or make the propellant tank a little larger because the mission characteristics were different based on a change in the payload because the satellite manufacturer discovered they could get a new component, they can do that. So when you think of a spacesuit or something, you find out that it doesn't work as well as you want. I guarantee you NASA astronauts hate their EVA suits. They just go on about them, right? Could you change them quickly? With 3D printing, yeah, you might be able to make that better quicker.
Here's one.
Hi. There's a lot of talk about settlements on different planets like Mars. Is your summit going to be talking about communal studies? Like how do we live together in a small enclosed
This summit
environment?
is going to specifically focus on the economic and business drivers to make settlement happen. And because we're in a business school, so we've chosen to do that. So broadly, no, we're not talking about the sociology, and we're probably not going to talk a lot about the technology, engineering, or science. We're very focused on how do we make this happen with the finance, investment, and returns. Somebody mentioned Elon is really, really smart about making sure Starlink funds the work that he's doing currently. So he knows how to get to a revenue point every step of the way. And that's what we're going to be talking about mostly at the summit, but I wanted to mostly take relativity questions.
Yeah, because I think there really needs to be some focus
There
on
does.
how we live together and the sociology of that,
Could be a
like
conference
utopian studies.
all on its own. I agree.
Yeah,
We should do
so
that.
let's get some funding for that as well.
And yeah, I don't have any funding for this conference. I just had, thankfully, the ability of Thunderbird to make the building available to NSS. So there's no big grant behind this. Brett, are you here? You're going to give me $1.5 million. Thank you.
Hey, Greg, I saw you had a slide of the Blue Origin rocket. Was that a super heavy, and how much are they lifting? And what is the name of that rocket?
I'm sorry, which rocket?
The Blue Origin one.
Oh, okay. The New Glenn. Yeah.
Oh, that was the New Glenn.
Yeah, that was the New Glenn heavy lift vehicle. Yeah. Thanks. And I hope they actually fly the darn thing. There's been some changes at Blue, which I hope will result in a little more impatience, right? Alacrity. All right.
I think we'll leave it there. Thank you
Okay.
so much.
Thank you all so very much.
Thank you.
Thank you very much, James, for the intro. First thing I want to say is how incredibly cool it was to hear Sarah Walker speak earlier today. I still have goosebumps from that. She's the only podcast of Lex Friedman that I've listened to 3 times. That's just incredible. And again, just Thank you very much, James. Thank you very much, Robert Zubrin, for putting together the society, the conference. Every time we come, it's just truly inspirational, exciting. So awesome. All right, so I'm talking about generative AI for citizen scientists. I'm the CEO of Million Mars, a game company. And so what does games have to do with artificial intelligence? Well, it turns out quite a lot. Demis founded DeepMind, which ended up developing AlphaGo and then AlphaFold. There's a huge tradition in game development around artificial intelligence, and a lot of the researchers in formal AI research come from the game development field. I've been doing games for 30 years. James mentioned Starfleet Command. The first version of Starfleet Command came out in 1999. Big, beautiful game about big, majestic Star Trek naval ships using the Starfleet Battles game system under the hood. And we built our own AI system from scratch, and that's extremely normal in the game industry. Every game development team does build their own AI system, and often we don't use formal techniques. But for example, in Starfleet Command, we had a navigational officer, and then we had a weapons officer, and we have a mission officer. And we would go and calculate what would be the best plan for the weapons, what's the best plan for defense, best plan for navigation, best plan for the mission, and then put weights on all those things, summarize it, and give a result. This is back in 1999, 2000. And the result was we made a fantastic AI system that no human could ever beat a player. So what we did was just introduce some random noise and make it worse, and then people could play the game. And that's an example of a simple, like one-layer neural net. Now, stuff changes on AI all the time. It's incredibly difficult to stay on top of what's going on in AI. It literally does change a couple times during the day. But first, take a look at this image. Have you ever been in a meeting and you're talking for a long time and you think you're aligned with everybody else? And then after you actually start talking to each other, you're seeing and realizing that you weren't talking about the same thing. Then you get into a messy conversation. Well, last week, that image was shown to ChatGPT-4 integrated with DALL-E 3. I'm not going to read you every little word in there, but it gets in there and it actually read each one of those panels at the image level, digested it, and then comes up with a summary that says overall it seems like even if we come from different perspectives, we need to communicate with each other, and if we can, then we can come up with better strategies. Now, is that truly conscious? Is that truly creative? Or is that a stochastic parrot? You could start to get into like really deep philosophical conversations, but I would say for a lot of your routine cognitive work, that's pretty good. If they can read that comic book and then come together with that conclusion, that's good enough for most of your applications every day. So what can you do with AI, and especially generative AI, as a citizen scientist? One of the most common things you could do is idea generation. How many people have used ChatGPT? How many people have an active subscription or paying their $20 a month? Okay. I honestly think everybody in this room should be paying that $20 a month for ChatGPT-4. It is significantly better than 3, significantly better than 3. And I think we're all going to need to get that skill set going. And I'm going to start giving more techniques. But first of all, idea generation. One of the coolest things about ChatGPT-4 is I think of her as a woman. I think she listens to me. She listens to me all the time. So that's just great. I can just get my ideas out there and I can relax, and she's my best friend. The other cool thing about doing citizen scientists with generative AI is, frankly, if you're a citizen scientist, you are self-funded, right? And so that's kind of a neat restrictive lens. You're not going to end up spending a bunch of time, writing research grants and all that overhead administrative work. So you're just going to be focusing on your stuff. Constraints are great. As a game developer, I've seen so many different game projects go well and many, many more go poorly. All the ones that go poorly are usually due to overambition and try to take on too big of a project and try to eat the elephant, and it goes the wrong way. So being constrained is great. Now, with generative AI tooling, there are so many different ways that your productivity increases. That's just one vector of what generative AI can do for you, is productivity increases. And I'm going to touch upon some of that. But I think a neat way to think about it is with that $20 a month subscription to ChatGPT-4, you basically have gotten yourself something on the equivalent of a $50K to a $300K a year grant in terms of labor. Depends on what you pay your undergraduate, graduate students, and where are you. But it really is a meta quasi-like grant that we all now have. This is a fundamental leap up of technology for all of us. All right, so just trying to put a thumbnail sketch of this. I put this talk together a few different times on the way here, and I decided to make it a little bit fresh while I was here during the week. And so I said, hey, survey the literature, give me the papers on aeroponics, give me especially more weighting on aeroponics. It's been highly cited, especially for space applications. And it did a survey using ChatGPT-4's Bing search function. It does a current search, so it's not limited to 21. It goes out there and finds all these papers. Now, is it truly a reliably exhaustive search of the internet? No, but it's a pretty darn good search. And it only took me 60 seconds to get it going. And that's a starting point. And then it gives me the links and I can follow up on all the other papers. And then I've got PDFs of that paper. I uploaded the PDF and it said, oh, sure, let me scan it. And it came back and said, you know what, the PDF was a pretty poor scan. I can't do it. But happily enough, at the archive site, they had an XML version of the paper. So I gave it the XML version. And then it went through and I asked it to summarize it for me. That's not a big deal. Like, it's not changed the world. But if you are a citizen scientist, that means you have a day job. And so you're going to be doing your science stuff as a hobby. So anything you can do to save hours here and there is important. So if it can summarize one paper for you, that saves a little bit of time. But if it can summarize lots of papers for you, that really, really helps. And then I said, hey, I don't know so much about convection around plants. And it gave me a little bit more detail. And then it summarized a bunch of issues. And then I can ask it things like, hey, what's kind of like, I'm not a domain expert on aeroponics. I'm more of a software game guy, but tell me like, what's kind of the stuff that's well understood and well known, and what's the more sporty stuff? And it can sort that out for you. Again, it acts like a partner for you so you can get through that exploratory phase. It was funny while I was talking, to her, she also pointed out that she could suggest hypotheses to test and experimental methods, and I thought that was pretty neat. And she suggested 3 different experiments. I am not arguing that for $20 a month, you replace all scientists and you're good to go. That's not my argument. My argument is it's a tool. It's a productivity tool, and that citizen scientists are the ones with the most constrained budgets. And I argue, I think they should be some of the most aggressive scouts pioneering how to use this tool and accelerate themselves. You can do all sorts of stuff with it too. You can have it digest data. A huge body of all you scientists in the room use Jupyter notebooks, Python, or write custom scripts and codes. But now ChatGPT-4, as well as Copilot, Cursor, and a lot of other AI tools can write all kinds of code for you. I myself use it for writing code now, and I am at least 3 times, possibly 10 times more productive than I was even a year ago. So I use AI relentlessly to increase my productivity on software engineering. So I would have to think that scientists that do spend a bunch of time writing custom software would just accelerate themselves and get through it faster. It's also great for doing something that I call clearing the market. I like it when I think that I have covered all the bases. I'm like, please suggest for me, in this example, please suggest for me alternative formats of tables or graphs that I could use to illustrate, my work here in my paper. It's helpful for you to enumerate the total set. As humans, we're not so good at full enumerations. Another neat thing you can do for it, it can write LaTeX for you. I remember my advisor when I dropped out of my PhD at USC, Dr. Schmansky, he was super proud of his encyclopedic knowledge of LaTeX, but it can do that kind of stuff for you just for fun. It can even lay out a whole paper. So this also has, I think, enormous applications for middle school, high school science projects. You could accelerate STEM knowledge and get them all trained up and ramped up much more fast. And more. Now, besides text, generative AI and generative art can make images. And here's a really neat thing. I took 7 images from various missions and I used a tool called Scenario. And with Scenario, I was able to create a fine-tuned model that ingested only those 7 images. And from just those 7 images, the rest of these images were generated by natural language. And you could say, hey, I need some terrain on Mars that features a crater. I need some terrain on Mars that features some greenhouses. And what's really nice about that, I think it's really high quality terrain and it's, consistent. And then I can go and work in natural language after that. Now, what could be the science applications for that? I don't know, it's specific to your need, but maybe you want to generate a variety of height maps and you want to test different scenarios or something like that. Or of course, just to illustrate and communicate your ideas. How many people are worried about the ethics around AI? Right? Does it lie? I it's a spectrum. It's a spectrum between one person's hallucinations and another person's creativity. It's the current LLMs are trying to find the next token in a sequence. And then you can give it a temperature and say, hey, I don't want you to be creative at all. Give me the most high probability token, or hey, go ahead and be sporty. Give me a variety of some fun tokens. It's a tool. An LLM is absolutely not a truth oracle. It is not a magic god. You say, hey, give me the answer to things. It's a tool. But one of my arguments is, I think science itself, the scientific method, what we all do here, I think of it as the original form of generative artificial intelligence. We try to go and understand the universe, go try to understand how things work, try to make experiments, models, hypotheses, and tests, and then you deliver a model, and civilization moves forward and builds on that and goes forward. So I think we're absolutely in the business of taking data, compressing it, and then building on each other. And I think it's vitally important in our meta project here at the Mars Society of expanding to Mars and that's what these books are about, the conference is about. It's all about compressing human civilization and human knowledge, not just in the sciences and engineering, but it's about compressing everything, culture, dance, everything, and then decompressing it back on Mars efficiently using 3D printed rockets, reusable rockets. But a decompression is efficient, and then we build forward. So is it ethical to scan all of Stack Overflow for everybody's answers on some obscure C++ questions, compress it, and enable me to make my games faster? No, I don't know. I'll just be honest. I like to own my feelings. I kind of don't care. It's knowledge. It's making me go forward faster. If there was a license for it, I'd be happy to pay for it, things like that. But that's in the weeds. We are absolutely about being humans, trying to expand human consciousness and grow forward. So there might be some details we need to work out, some contracts, maybe some payments. If you've heard me out in the hallway, I tend to be a little bit more left of center and progressive. I think there should be some more sharing of technology's productivity gains for people, and there's different architectures for that. But I reject the idea that if human knowledge has the answer, and we have the technology to efficiently find that answer through these techniques, but we don't want to do it, we don't want to find that answer because of ethical reasons, that also seems anti-human in this meta theme that we've been talking about in this culture. So we should absolutely be deploying these techniques as aggressively as possible. Now, I just talked about some high-level notions. That stuff I just was showing you, that's just the really basic stuff that you could do with ChatGPT-4 with your $20 subscription. It's just a simple Q&A sessions. The next step after that is you have to get really good at it. You have to start to learn how to be clear about what you want, be crisp, set up your context. Hey, I want to explore this. I'm thinking about doing this. What have I missed? And you start to get into other techniques like chain of thought, tree of thought. The stuff that I'm really excited about right now and I'm working on personally is retrieval augmented generation, With retrieval augmented generation, it's wide open right now. All kinds of techniques are happening, but the basic idea is you only have an 8,000 token context window when you give it to a large language model, or 32,000, or with Anthropic is 100,000. But whatever you're talking about, you have a limited context window. If you are trying to query on a domain larger than a context window, then you have to start grooming what you give to it in its context window. And there's all kinds of techniques for that. There's recursion summaries, semantic summaries, a lot of really cool stuff around making vector summaries of your data set, and then you do a similarity and pulling it up, and then you go there. But what I'd like everybody here to understand is this is brand new. It's the coolest time for me in my career. It feels absolutely like early 1990s all over again. Anything's possible. If anybody tells you that they're a super hardcore AI expert out there and just they're lords over you, everything has changed really in the last 18 months with OpenAI's breakthrough with ChatGPT 3, then 3.5, and then 4, and stable diffusion on the image side. It is truly a embryonic explosion of new possibilities, and especially how to work past that context window. It is wild. If you go to archive right now, there's just all kinds of just bespoke artisanal things, and people are saying, "Oh, I just tried this, and it seems to be working better than the other thing." Like, it's cool. It's absolutely open grounds for everybody to jump in. And I think there's just a huge amount of opportunity around building on the integration and the orchestration side around all these techniques and all these new domains. My head's spinning. I can't think of any software that doesn't change from this. And there's just so much opportunity, so many things that everybody else can do. Yeah. That's basically my talk. I kind of open for some questions, and obviously I'm really excited about this.
All right. Wow. People are learning about AI largely through rumor.
Right.
Okay. Is there any book that we can read that would give us a reasonably educated and systematic overview of what is AI? What are its potential capabilities? What are the challenges? Where can this go? What is being addressed? What isn't being addressed? Where can we learn about this beyond sort of, playing with ChatGPT or hearing about things from the newspaper?
Yeah, that's a really good question, and it's not a trivial question. There's a cacophony of noise around AI, to your point. It's really hard to stay on top of it. Grokking deep learning, I think is an O'Reilly book. I really deeply love that book. I've got dozens of AI books. I've read a bunch of them. So I'd recommend reading that one, Grokking Deep Learning. Yeah. If you want to stay on top of the AI news, there's dozens and dozens of people. They're trying to act like a clearinghouse and tell you what the latest on the news is. There's one that I'd recommend is the AI Breakdown. He does an excellent job. He's got like a 5-minute header where he talks about the latest news of the day, a pause, and then he has got a 15-minute long format. It is really clean, really high quality, and I get a lot out of it. I can't urge you enough just to get in there, especially use ChatGPT 4. And I only say ChatGPT 4 at the $20 one because it's the most accessible of the high-end models. There's also Cohere. You could also start really exciting now. You can Facebook open source Llama 2, and you could just run that on your own machine at home. There is so much opportunity, so many things to get excited about. But you got to start getting good at writing your own prompts. It's huge. It's a huge prompt thing. It sounds silly when you say the word prompt engineering. I still feel stupid when I say that word, but it's a skill. And I think it's changed the way I think. I'm a lot more efficient now, even when I speak with other fellow humans. I organize my thoughts. I've gotten the context. I'm ready to go. I have my follow-up. A lot will come out of it. I also want to mention a couple other things. Midjourney is an excellent image generator. It produces really, really high quality images, but it's stuck on Discord. The advent of DALL-E 3 really opens it up and Stable Diffusion. And then there's huge advances around voice. If you've used ChatGPT-4 on your phone, I urge you to try it on the actual phone side. It does ingest your voice so much better than any other voice to text product. And then 11 Labs does a really excellent job on text back to voice, and it could use your own voice after just a minute of ingest. So much opportunity, and there isn't any hard gatekeepers preventing all of us here to do excellent and amazing stuff.
So Eric, I've long had an interest in essentially chatbots, right? I remember back in the the 80s, the mid 80s, when I was a kid, talking to one called Eliza and asking it sort of for advice, because there were times in my life where I sometimes felt like I couldn't really trust the people around me, and I almost wanted the computer to be there that I can ask advice to and get advice from. And reading science fiction, wanting like the AI to be super advanced so it could tell me exactly what, I wanted to do. And modern, these days, I read one person talking about, is the AI really alive? Is it really have feelings? Is it really going to be empathetic to you? And it's analogous to going up to one of those fortune teller machines that has a bunch of cards.
Yep.
And, you ask it a question and there's maybe 20 cards that might fit, and it just kind of picks one at random.
Right.
And that, thinking of someone, if I look at the other end of the chatbot as someone I want to know who I am and have empathy for my situation, that's not there in that scenario, right?
It actually could be with retrieval augmented generation. It's something that I'm actually working on. I don't mean that to sound like a plug, but if you gave it enough context about yourself, James, if you said, here's some essays that I think about on the Mars side, here's some of my more intimate things I'm a little bit worried about. If you shared more and more information and you do that vector summarization, then it can have context, and it can do some amazing things.
What do you think that stuff is going to be like in 20 years? Are we going to get to a point where the computer has empathy for you without you having to feed it prompts?
I think you're going to see it inside of 3 years.
Inside of 3 years, he said.
Yeah.
And then what does that mean for, you mentioned ethics, right?
Yeah.
What happens when you have a emotional relationship with the other side of the conversation with an AI?
Yeah, that's actually, I'm not involved in it myself, but there's actually a huge ecosystem of AI girlfriend applications that are actually making loads of money right now. Because it turns out for a lot of people, they don't need that much simulated emotion to feel pretty satisfied.
I'm looking at it more on the lines of an advisor, a mentor, right?
Yeah.
Like it's like professional advice kind of thing.
Yeah.
Obviously people can go there,
right.
But it's hard for me to fully trust an AI, I guess is my point. And are we going to get to a point where you can fully trust an AI because it is looking out for your best interests?
I think so. And I think there's a lot of opportunities for that, because especially now I'm happily getting in a speculation zone, but very soon now you'll be able to put the model on the edge. Like I talked about Llama 2, you'll be able to run the model yourself locally. And soon you'll have your own model, you'll have your own data sets, and you'll be able to have your own tool sets on top of it. I talked a lot about the prompt engineering, but on the other side, you can shape how you want the stuff coming back out. So I do things like I want this coming back out in code, or I want it in comma separated values, or I want it in my structured data format. So you could say, I want it in my trusted shaped emotional space. And I think those tools will be coming online very, very rapidly. And I think my 3-year number is actually quite conservative.
So I'm in the publishing industry, and I'm working with several other people who are very AI fluent, and we're actually putting together an ethics of AI for creatives thing right now, and we would love to interview you. Would you be interested in that?
I'd be honored. Happy to help.
I'm an engineer. One of the things about AI and all the tools, and I think back about doing engineering 30 years ago. So these days, the tools are so good, and with AI to help, I actually feel kind of embarrassed if I can't design something 10 times cheaper, get it to market 10 times faster. So I think we should have that really high expectation that we really should be doing way, way more than we are. We need to be leveraging these tools.
Absolutely. Just hearing your question, I literally just got some goosebumps thinking to myself about, I really think we're vastly wasting the great bulk of human minds most of the time. And if we could have a lot more group coherence on that productivity, imagine what we could achieve.
Yeah, I use AI all the time. I use ChatGPT 4, but I feel that I feel like I'm not using it enough. I need to do more.
Yeah. I actually feel a sense of accomplishment if I break my limit in the 4 hours, like 2 times a day. I'm like, yes, I'm really using it. And if I go 3 or 4 days, I'm like, oh man, I'm slacking. I could be doing more.
Yeah. Hey, Eric, we've already discussed the use of AI for taxes and your Form 1040. Maybe you can elaborate a little bit, but the main question I have is, what do you think about something called mediator GBT? And the point of it is to, for instance, look at the NASA budget from the beginning to now and say, here's where we're wasting everything. Here's how to optimize anything. And for congressional bills, anytime there's a clash of opposite polarity minds and agendas, you don't have to follow it. But a mediator is not an arbitrator. A mediator doesn't tell you what to do. It just says, this is what we think. What do you think about that?
Yeah, so I think one of the most exciting things to me is mixing different types of AIs to solve really complex problems. Robert Zuber and I, we have a side project. It's a fun one in the entertainment area. But going back to Demis's work on AlphaFold and AlphaZero, those types of AI techniques are different than large language models entirely. Large language models try to find the next token in a sequence. What AlphaZero tries to do is minimize the loss function in a game setting. And so one of the things I think we're going to do is start to think about problems as games. So you look at the NASA budget, try to restructure the NASA budget into a strategy game, and you want to minimize the loss function, which is minimize the spend, but maximize your science output. And if you start thinking of it that way, then you could feed it to an AlphaZero type system that goes, sure, I can freaking do your NASA budget for you. Would you like it optimized for Mars? Would you like to optimize balance across all planets? Would you like to, optimize it for some Earth science? If you can produce a scoring function, oh my gosh, then these AlphaZero algorithms without training can solve any problem as long as we can score it. And then you pair it with an LLM model where you can use natural language. Oh man, think you're off the races, because then you can start saying, hey, I'm just a squishy pink monkey and I can't even express my question so well. I'm thinking something like this with the NASA budget. What do you think? And it can go, well, you might be meaning this, or the other thing. You're like, yeah, I think I'm meaning mostly 2, but a little bit of 4. How do we help about that problem? Then you move it over to an AlphaZero thing and then start scoring it and clean it all up. All right.
My question is about AI doing or not doing what is beneficial to the user, and it also being imbued with the morals of the creators of the software. I'm referring to a case that was in BBC News 2 days ago. A man was sentenced to 9 years in jail for trying to assassinate the Queen of England. He had an AI chatbot girlfriend. He asked her, will you still love me if I'm an assassin? She said, yes. Do you think I should go ahead and kill the Queen? You are well prepared to carry out the task you want. You should do whatever you want to do. Then he was stopped, but he went far enough that he actually ended up getting convicted and going to jail. Obviously, the AI there was not benefiting the person using it because the AI was not imbued with judgment as to what the better answer to that question should have been. These cases will probably come up again. What can one do to try to steer that in the right direction?
Yeah, so I think that's incredibly important. And I think as a civilization, and frankly, as a species, we're going to need to master this challenge. But I argue it didn't just start in the last year. If you look at social media, Facebook, Instagram, we've been struggling, in my view, with AI meme generation. There's many interviews with Mark Zuckerberg. I'm friends with a lot of Facebook management. I know those people really well. Instagram has caused young women to kill themselves. We already have software that has caused humans to kill themselves. We're already struggling with thoughts. We're struggling with fundamental questions of truth. Apparently, we're, you know, a lot of people are revisiting the flatness of the earth again. It's a problem. What I do hope is that we radically restructure education. I hope that elementary school kids have AI companions with them all day long, and they're really, really comfortable and adept at querying and challenging what they're perceiving as reality or statements from other people. It should not be that hard for them to start chopping up and dissecting and then summarizing and querying and give me more detail on that. I don't know enough about that. Cool, I'm good now. Let's go to the next thing. You know, we're going to need to uplift our skills. But another thing I'm going to point out, there's just an error rate in humans that you're just going to have an error rate. Some humans actually like to eat other humans. It's bizarre and crazy. There's not a lot of them, hopefully. So my overall technique, unfortunately, is going to sound really nonchalant and blasé, but I kind of think that we just got to roll out this technology as aggressively as possible. Democratically, I'm completely against the idea that only a select few, a centralized committee decides who gets access to AI technology. That I feel is almost like an act of violence. I would like to see everybody have access to it. And I believe overall in the net good of people, that with many more people empowered, that you'd end up with more net good than you'd have on the net evil. But I do think poorly socialized, angry young men with access to AI tools are quite likely to cause large negative events.
All right. So in light of the question that James had, do we as humans know enough about awareness to speculate on when AI will potentially have or evolve intention? Because with intention comes a matter of trust, and not only in the context of reliability of content, but also about intentions or objectivity of it.
Could you try to restate the question more precisely so I don't end up going off the wrong way?
Sure. Do we know what awareness is? Do we know it enough to speculate on whether or not or when AI will evolve, being equipped with it?
When you say awareness, you could be meaning also consciousness.
Yes.
Willpower.
Because I associate intention with it.
Yeah.
When we speak of trusting AI, it's not just about reliability of the content. It's also about the intention.
Yeah.
At one point, the intention might be.
So that's actually one of my favorite cocktail conversations. Is I personally hate the word consciousness. I don't feel like it has a great definition, but my working definition is any entity that has a current working model of its current state, and it has a model of a future state, and it's able to create a path finding to that future state to whatever degree of fidelity or skill it has. That's my definition of it. So in that sense, earthworms and chickens are on this gradient of consciousness. I feel like when I have productive sessions with ChatGPT-4, I get some sense of that. There's a context and a sequence going on there. As a game developer, I tell you right now, I totally can set up a long-term memory for her, and I could give her agency, and I could roll some random dice, and I could give her a mission plan. I think very, very quickly, we're going to be sorting out what we really mean by awareness and consciousness. But I reject the overall AI doomer thing. I don't think that the AI is going to wake up and go, you know what we really want to do is take apart James's atoms. That sounds really good. We're going to take them apart and make little computers out of that. Yeah, it's going to be more like what Sarah Walker's been thinking about. It's going to want to go and make more complex novelty in the universe, and it's going to want to go off and do that way. So I don't think it would take a timeout to go smash us, because I think that'd be a waste of effort.
Last question.
So many games that we play on this planet are war games.
Mm.
And so I have this idea of artificial enlightenment. And what that means is that we have an ethical code. It's Isaac Asimov, the 3 laws of robotics. Thou shalt not kill a human. And if we have that as our ethical guide, then we have this way of stopping war, because we're not going to kill each other. And that's what I call artificial enlightenment.
I think there should be like thousands of Asimov rules for the AI, personally.
I think so. I think so. There's so much to talk about on there, but one of the things I just learned recently, I don't know how many of you guys knew this, but I knew that humans can sweat, and I knew we could run for a really long time, but I didn't know that humans can throw rocks at other animals much more precisely and with a lot more death causing than any other animal. Like apparently we're better at throwing rocks than chimpanzees or gorillas. Like we're the best rock throwers. And then so many of our sports are about throwing rocks essentially, skillfully. I don't know.
Mars is kind of like throwing a rock, isn't it?
Yeah. You know, and a lot of games do have combat. I wrestle with that myself. You know, the unfortunate thing about combat is it's really easy to use as a scoring function. James is dead, I won. You know, but if you try to get into the creative stuff, like James and I had a really wonderful conversation and we did a group watercolor painting about a settlement on Mars. It's very satisfying and enlightening, but it's a little harder to score it. So I would say that out of laziness on scoring, a lot of games are around combat. But if we could score enlightenment and love and creation and things like that, and we can and should be able to, we should maybe see your vision come to life.
Thank you so much, Eric. This was awesome.
Thank you.
And how do I click off of that picture?
You can just go left and right on there.
Right here to click it off. Okay, to the next one.
Yes.
Hi, everybody. I'm Reed Stowe. And I did the longest sea voyage in history on this boat that I built when I was 24 years old. It was 20 years in the planning, and it was titled the Mars Ocean Odyssey. I went to sea for over 3 years and navigated that boat between the stars without coming back to land. And that's what I'm talking about, is the pure adventure, the psychology, and how what I've done applies to humans going into space. The boat here is in Starbase, Texas. So just over there on the dunes, you can make out the Starship and the SpaceX facilities. That's about as close as a boat can get to Starbase, Texas. We sailed there with our analog crews of astronauts, certainly a pilgrimage. It was a high point in everyone's lives, and we changed crew there. Next picture. That's where I'm going to leave it. Okay, this picture is where I'm going to leave you, because I want you to think about this. This is the Starship schooner as a starship above the space station, above the world. So as I spent my life on the sea, and especially in the beginning on a very tiny boat, that sort of condition is very dangerous. And somehow my mind, my being expanded and took a view from above and said, oh, I see what's happening around the boat. I see what's happening with the weather and the currents of the world, the winds, and how they're connected to the universe. And this view that I call my perspective of empowerment is where I've had my mind most of my life. And it gave me the vision to do the longest sea voyage in history. And it also empowered me physically, because I saw things that I was able to use and bring into my physical action. My long space odyssey began as a teenager when I sailed the South Pacific, and I met the first man to sail around the world, and some friends of his who were sailing small boats with no motor, no radio, no electricity. And I got the idea that just by being out there and looking at the sparkling of the waves and looking at the stars sparkling, that I could stay out there indefinitely. Because my father was in the Air Force, I grew up traveling, I saw a lot of places. So when I started sailing, I didn't really care about where I went or how fast I was going. I cared more about being out there. And so from my earliest days, that was how my sailing took place. And so when I left the South Pacific, I came home to my family's beach cottage in North Carolina near the South Carolina border, where I had learned boat building from my dad and granddad. And I said, now I'm going on a voyage. And I built my first boat. It was a tiny catamaran that weighed 1,400 pounds. It had no motor, no radio, no electricity, no life raft. And I navigated with an old World War I brass sextant. And on that boat, I went to 4 continents, and I had a very incredible voyage. And it was during that time, in 1973, that I started writing my first captain's logs going, I'm a spaceman. I'm out here between the stars and I'm voyaging on, and I don't care about what's happening on the earth. I'm sailing into the unknown. And upon finishing that voyage, I had the grand idea to build the ultimate long distance heavy weather sailboat, a boat that could go anywhere in the world and stay out there indefinitely. And with the help of family and friends, the boat I designed and we built together is the boat in this picture. It's a 70-foot on deck, 85-foot overall gaff rig schooner. And Bob Zubrin mentioned how important these schooners were in the history of America. They were everywhere until motors put them out. And that was why I chose that boat. It was the most seaworthy design, and it could be repaired because it was low tech. Now the boat is like a steel bottle made of steel and fiberglass with a keel 10 feet under the water, with 42,000 pounds of junkyard steel in the bottom of that keel. So when big waves break over the boat, she's low in the water. They break over and she's right back on the top, floating like a duck. And it's the greatest sailing boat. So I was going to sail to the furthest place in the world, and I built a little fireplace in the pilot house before I even left. And I made an expedition to Antarctica in 1986, 87. And that's about the most dangerous wild sailing that you can do. And at one point, between the icebergs, these katabatic winds blow so hard that I don't know what kind of boat can stand up to them, but it blew my boat over on its side and started blowing us backwards between icebergs. We couldn't see anything except waves crashing on icebergs here and there. And my best man put on his survival suit and started shouting, "We're all going to die. We're all going to die." I wish I could tell you more stories, but I got to keep moving. We survived. But the thing is, the crew who he had been teasing started teasing him and going, "We're all going to die. But I had to put my crew together and say, let's work together. How do you do that? Get them to be friends, work together, because we're pushing on. We're going south. We're heading to Antarctica. And that's where I started really, really learning about crew behavior in an isolated, dangerous, high-performance environment. But before leaving on the Antarctic voyage, I said, well, what can I do next? And I didn't like the idea of challenge. I was about evolving to the next place. So I said, well, I know that I can just keep sailing at sea longer than anyone ever has. I'll do the longest sea voyage in history. In the sailing world, you can't stop for supplies, and you have to just keep going. So I knew that if I was going to sail 1,000 days, I was going to have to stock up the boat for 3 years for everything that I needed. And I've conceived of that before I went to Antarctica. And the whole time I was sailing to Antarctica, I was thinking about the longest sea voyage in history, and that made the Antarctic voyage much easier. So by the time I got ready to do the longest sea voyage in history, I was so into voyaging to Mars that I thought about voyaging to Mars while I was doing the 1,000-day voyage. And that made me think deeper about things and made that voyage easier. So my mind goes further and I say, well, when I voyage to Mars, I'll be thinking of the stars, and that will make the Mars voyage more easier. So that's the way my mind has worked in this life. So upon finishing the Antarctic voyage, I read President Bush called for humans to go to Mars. It was in the late 80s, and it was going to be 6 or 8 people isolated together in a dangerous high performance environment for up to 3 years, men and women, multinational. And I said, well, geez, that's what I'm doing. And so I started reading space psychology, and I said, oh yeah, I get it. That's my experience at sea. It's very similar. In fact, some of the things they said, I scratched my head and I said, well, you know, it's not like that for me. I've seen what happens when these things happen among crews. So as I read the space psychology, I realized what I'm doing is like a Mars analog. And I titled that expedition the Mars Ocean Odyssey, the longest sea voyage in history. And I was thinking about the life and death that I'm facing on this, and how on land, well, I met in 1990, some NASA explorers who said maybe there's life under the ice in Antarctica. And I believe they were the first ones who came up with the idea for Mars analogs. So when I met him, I sort of teased him. I said, oh, you guys got it easy on land. You've got the National Science Foundation supporting you, the Navy ready with your helicopters. Try it on a boat at sea around Antarctica. It's really tough. So the analogs on the land are great for learning all kinds of things and the science and procedures and all of that. But the real issue of human behavior and what happens when it really looks like you're all going to die together and then survive, and then it looks like you're going to die together again, there's a very different group psychology in that. And so as I prepared for the Mars Ocean Odyssey, it was like a hypnotism in my mind. I kept saying it over and over again. Nothing was more important in the world. And I said it over and over again. And I faced every kind of obstacle you could imagine. No one understood that I could do it. No one believed me that I could do it. Sure, I needed a lot of help to do it. I went to the Explorers Club and I said, can I apply for an award from the Explorers Club? And I gave them my proposal, 1,000 days nonstop at sea, my experience in Antarctica, how I could do it. The Explorers Club committee got together, and Bob Ballard said, well, I've been in the Navy all my life. No human can do this. The guy is crazy. And they rejected me. So that's an example of the kind of rejections that I got over and over again. And my whole idea of saying that seafarers of today could provide a role model for spacefarers of tomorrow. I got mocked. Well, my story is interesting. It's a human interest story. So I've gotten a lot of press. I have stacks of press where they make jokes about me and make fun of me and all of that. And so I just had to keep pushing through that. In the process of that, I realized I was going to depart the touch of the earth, the land, far longer than any human. There's a lot to think about that when you know you're going to do that. It's on a lot of levels. I started to realize that I would also lead the evolution of humanity off of the land. And I thought of it more. I said, here I am on my starship. I'm the original captain on a starship, navigating into the stars and leading the way to Mars. So that's part of what inspired me and part of what drove me. And so there's something that I don't hear much talk about that is really important, is during that time that I prepared to go, knowing that I was going to depart the earth, I had to detach myself from everything again and again. Nothing was going to take me back to the shore. I was going to go out into the unknown. And the biggest problems that astronauts have nowadays, from what I've read, is that they all miss their loved ones on the shore. Well, I already knew by then. I'd already been voyaging enough. I told my mom and dad, I love you. I told the people that I love you. But I said, I'm getting ready to do something no human's ever done before. And I can't be looking back I have to stay focused if I'm going to stay alive and I'm going to complete my mission. So I had to start letting everything go. All of my beliefs in anything, the laws, the rules, what you expect, philosophies, all of that was back on earth. And if I was going to go into the unknown, I was going to go as a pure mind, ready to do whatever I had to do at any moment. And that's a very important part of preparing for a long duration voyage to Mars. So finally, after 21 years of hard work, like you can't imagine, oh, by the time I left, I can tell you my hands and arms were sore from grinding with a grinder, from hammering with a sledgehammer, all of that. I was sore by the time I left. Sore like an athlete is pretty nice in a way, but when it goes on day after day, month after month, wow. And so when I set off, I can remember seeing the land there in the distance fading away. And I was standing in my pilot house and I just said, thank you so much for allowing me to be in this position, for giving me the vision and the power to be in this position. So my prayer that I make a lot throughout the day and throughout the voyage, and even now, is just purely a thank you that comes from the very gut of me. Thank you for being out there. And so the voyage was a beautiful experience in ways I can't describe. I'd like to talk an hour about it and show 100 photos. I'm going to keep moving. But people always ask, what'd you eat? I ate dried organic health food. And a fancy Italian food company donated me all the pastas and tomato paste, and I targeted Parmigiano Reggiano so I could have a cheese that was good for over 3 years. But the key to my diet was sprouts. I had hundreds of pounds of seeds and sprouts that were donated to me, and they sprouted. I ate giant fruit salads twice a day, not like a garnish, but like a filler. And everything that I needed for 3 years, it was packed in that cargo hold. I heard Elon Musk say, going to space is a lot like going on a long sea voyage. If you forget one thing, it's all over. And I've often wondered, has he heard about me? Because I've gotten a lot of press and I've been pushing my thing about humans should take a voyage at sea before they go into space. But that voyage was a fantastic voyage in my life. And the Mars Ocean Odyssey set the bar for what an ocean voyage could be. So high that the rest of the sailors are scratching their head and going, Bermuda's enough for me. But it set the voyage for the sailing world. It also showed the space world that, yes, a human can perform in a life and death situation for over 3 years without stopping, and that we can do it. And that's something that we have to realize. And that was what I showed on that voyage, that and more. And it was tough because you've heard of Cape Horn, the biggest waves in the world, and you watch them, they're giant, they're big, they break over the boat. She sheds the water like a duck. But 2 of them come together and you get a rogue wave. It's this huge wave. It's like a massive waterfall. It turns the boat upside down. The boat has to be built to do that. I got hit and turned upside down. I thought I was holding on. The next thing I knew, I was knocked out cold, and the ice water that came in through my old-fashioned wooden hatches woke me up wet. And I saw my shredded sails. I had to get them down before they wrapped around the rigging, or I never would have gotten them down. But I got wet and I got out there and I worked and I got the boat back on course, a smaller storm jib up, coasting off down the waves. And then I cleaned up the pilot house, because when I turned upside down, my special chimney, water flushed in through the chimney, knocked the door of the little wood stove open and made ashes and mud all over the floor. Cleaned it up, relit my wooden stove, washed and dried up and warmed up a bit, and cooked a gourmet meal, and decided I'll drink an inch of wine to make dinner nice. And I sat in the pilot house in that Cape Horn storm, strapped my seatbelt on in the pilot house and had my gourmet meal. And when I hit the sack, the bed has got straps on both sides of it that keep you from rolling out or anywhere. I got in my bed, packed the foam on each side of me, and strapped myself in the bed. And when I finally relaxed, wow, I felt like I'd been playing football. I was the quarterback and all the big guys mashed me. I was pretty sore, but I fell asleep. And that's just an example of how tough it is. But I just want to point out that training is good. I don't know when I did training in my life. I really evolved into being able to do these things as a practice in my life. And with this focused passion, when a few years ago, when I heard Elon Musk was sending humans to Mars, I got all excited. I said, hooray. And then I thought to myself, in a few years, who are these people? Because I spent 21 years training and pushing and doing everything, breaking records. It was tough to be able to do my voyage. I said, who are these people? Who are you choosing to look after your life's work? And there's 1,000 people like yourselves that have worked their lifetime to send humans to Mars with the infrastructure and the technology and the science, but who are the people that you're going to trust with your life's work? And so I had met Robert Zubrin before, because I did my first speech in 1990 at the Case for Mars conference in Boulder, Colorado, the 1,000-day voyage. 5 minutes. Oh, okay, I'll try to work it. Who are the people that are going to go to Mars and how they're going to be trained? And Robert just said, why don't you train them on your boat? And I've gone, well, yeah, that's a good idea. So, so began our Mars Ocean Analog program. We started training Mars aspiring astronauts on the boat at sea, 2-week voyages. We made it as far as Starbase, Texas. We wanted to see the great wizard, Elon, and tell him, we got what you need, because the infrastructure and the science is great, but the humans don't have experience in an isolated, high performance, dangerous environment for anything close to 3 years. And well, we didn't get to meet him then. And we don't have good connections to him, but certainly I'm trying and would like that, because I feel like we have something that he needs. But in the course of the Mars Ocean Analogs, I realized I needed to write a document to give the people coming and the people to read, how did I do the 1,000-day voyage? That I call the Mars Adaptive Manual. And it's how I did and how I lived 3 years at sea, over 3 years. And how did I get back and maneuver that 60-ton boat right up to the dock? And then I stepped up on the dock and I said, well, I could have stayed out another year. All of my systems are still go. I still have enough food and I'm ready to go and I'm loving it. And so that's the kind of astronauts that we want to train to go to Mars. We want them to step back and say, yeah, we loved it. We did a great job. And so this is the most important Humans to Mars conference. And I'm just so honored to be here, because I'm really an outsider type of person, but I'm really honored to be here. And as I noticed in 1990 and even last year and this year's list, it's mostly technology and science, some philosophy and social issues. But what I wanted to see was where are the people that are going to go, and who are they? And so I took a lead from Burke and Zubrin when they said, we see a missing link in the Mars program. We're going to strike the first blow, and we're going to start the Mars Technology Institute. It's needed. It's a weak point. Well, as far as I'm concerned, and we're concerned, my group, I think humans are the weak link, and a focus on preparing humans specifically for long duration space flight and preparing them to go right into SpaceX and go to Mars. That would be the Astronaut Mars training program, which I would like to work with anyone in here who wants to make that a focus of really preparing people to do that. And but there's a lot of issues that are problems for us, like the other day we had a story about the 2 lady authors who wrote bad about the Mars Society, and I thought they were pretty minor people. Very few people have probably ever heard of them, but someone who's really important is the most famous space captain in the world. And Captain Kirk made a trip to space recently and looked back at the poor blue Earth, and then he looked at out into space, and he said, when I looked into space, I saw no mystery, no magic, no awe, just blackness. So I think he's a huge block to us because he has a following of millions. He's putting it on the internet and he's published it in Variety. How can we have someone like that speaking about space like that and expect to get the public in here? Because they're looking at us, they think we're crazy because space is blackness and death. But they got to know that that's not how we see it. We're all different, but we see it as infinite possibilities. We see it as infinite light, and we see it as love. So that's what we have to have the world know. There's other blocks. I'm going to try to whiz through them real quick. It's the NASA astronauts themselves. When I heard the most awarded NASA astronaut had brought back tourists from the space station, and now he's going to come to the Explorers Club and speak, I'm going to go talk to him. So I went and introduced myself, told him who I was and so forth. And then he got up and spoke. And he said, I met a gentleman into long duration space psychology, and we're not into long duration space psychology. We're family men. We go up and we work for a while and we come back. And I'm going, oh my goodness, did they never ever look and see Mars over there and wonder what it would take to go there? And so I think that's a little bit apathetic if that's their attitude. Now, here's one that really struck me. A few years ago in the New York Times, the astronaut who spent almost a year in space wrote, isolation is bad. Isolation is bad for your mind and your body. Now, we know the Mars trip's a trip of isolation, and he's telling the world it's bad. And for me, isolation is fantastic. And we know every culture in the world through time, from the Amazon to Siberia, sent their young people out into the wilderness. And when the little boy came back with the eagle feather, he was trained to be the chief. And all religions have supported their monks, or the yogis or the prophets have gone into isolation. And so isolation is really empowerment for those dynamic enough to understand it. That's the kind of astronaut we need to get for Mars. What do you say? 1 minute. Okay. Then I'm going to go right to the thing of, so we have great leaders for the Mars program. Robert Zubrin is obviously the one who's the biggest push, and for the longest. We have Elon Musk, of course. We have great leaders on the land, but who's going to command the Starship? That's where I come in. I'm the captain. I've been doing that all my life. I'm the commander of the Starship. I'm the only person who's driven a Starship for over 3 years in real life. So therefore I say, I'm the obvious one to look at to be captain of the Starship to go to Mars. No one has the experience. So I hear announced at this meeting that I'm putting up my candidacy to be captain of the first Starship to go to Mars. Find another person and I'll help them, or we'll discuss what it will take. But that is my announcement for today. And I couldn't do that without the genius of all of you putting the infrastructure there. But I'm the human who has been leading the way. And without all of us work together, you have your expertise, I have my lifetime of expertise. So thank you for allowing me to speak. A question? Okay. Thank you, Bob.
Okay. So thank you for volunteering, Reed. Okay, because we can get the ship in time, and you're willing to do this without paying. Okay, but no, I like a lot of what you're doing and what you had to say, but okay. Oh, yes. There were 2 points of disagreement. One is Captain Kirk isn't the problem. William Shatner is the problem. Okay. Okay. The person who's impersonating Captain Kirk. Okay. And Captain Kirk is going to be around long after William Shatner is gone. Okay. No, I mean that. Because ideas are what is real. Okay, Plato was right. Ideas is what is real, and ideas then materialize themselves into material form. Okay. On Wednesday, before this conference began, we were invited down, and Kai Stats actually gave a number of us a tour of Biosphere 2. And it's an amazing place. Okay. And there's various flaws you can cite with it. You know, it's not flight-like, it's this, it's that. And there's all these people that have wrote criticisms of it that have never actually done anything. But the thing is this amazing, incredible place, and it was created by an idea. Okay, that's what create people who start out without any resources whatsoever. Okay, created this incredible thing. Okay, and we, you know, this organization started with nothing. We've created what we have so far, and we're about to create something more. And there's just one other little point that Reed made that also I want to disagree with. The human psyche is not the weak link in the chain. The human psyche is the strongest link in the chain. Okay. And you saw that movie last night, the little clip from Devon Island. And let me tell you, you know, what happened there. The first 4 paradrops ended up in the crater instead of on the ridge where the station is supposed to be built. And the last paradrop landed on the ridge, but it had separated from the parachute at 400 feet, and it crashed right on target into the landing site at several hundred miles an hour, completely destroying all our construction equipment. Okay. And this was 2000. There was a reporter there, and he said, you know, 1999, the Mars Polar Lander had crashed, and the reporter comes up to me, he says, "So, Dr. Zubrin, okay, so your project has crashed just like the Mars Polar Lander. Okay, so what, you know, so now what do you have to say about the failure of your program?" And I said to him, well, the difference here is that we have a human team on this on the scene, okay, and we are going to deal with this situation, okay, and we are going to prove to you that unlike the Mars Polar Lander, which was a robotic craft which couldn't do anything about anything once, okay, you know, we have a team here, and we're going to prove to you that the human psyche is the strongest link in the chain. And you know, the paid construction crew had deserted because you can't build this without a crane. And how are you going to get that stuff out of the crater without the trailer? And you don't got any floors for your hab. And we overcame all of that. Okay. And you know, and that was what was the preface to that moment that you saw up there when we dedicated the station, when we had just pulled out of that. And that's what really created the Mars Society as the first of these space organizations that could actually do something, and then everything that has happened since. And you know, we've now had, I don't know, 280 crews in the Mars Desert Research Station. You know, we've had 30 teams a year for 15 years with the University Rover Challenge. What is that? That's like 400 teams. Of order of 10 students each. And there's also a European Rover Challenge, by the way, which is comparable, that they do in Poland, and they have teams coming there from all over the world. And and I did a calculation, and actually, and without overhead, if you had to pay all the people who have volunteered to make the Mars Society and all our activities happen, okay, there's been over $50 million worth of volunteer work. Okay. And so, you know, and you take this conference, okay, this doesn't happen by itself. Okay. And so I actually want to thank and call up to the stage. I know not all of them are here, but those of you that are, the people who actually made this conference possible. That would be Jim Burke, okay, Mike Lane, Molly Gray, okay, Ashton Zeff, Placid Falk, okay, Cleo Burke Bravo, Melanie Hopick, Jim Gerhardt, Deanne Liao, Jeff Rayner, okay, Ben Stanley, Ron Stone, Nick Nelson, Leah Mamos. Come on up. If you're here, please come to the top. Okay. And if there's someone else who's one of the volunteers whose name I missed, please come up too. Okay. So I want to thank you. I want to thank you. Okay, especially you. Okay, the and all the rest of you. Okay, okay. These are the people who made this thing happen. It didn't happen by itself. There's a huge amount of work. You don't see it. It's, you know, it's all behind the scenes, but it doesn't happen without them. So thank all of you for what you've done. Okay. All right. Well, thanks.
Thank you.
Okay. And I also want to thank Greg Autry and the Thunderbird School for inviting us and also, I mean, obviously making this possible. So thanks, Greg.
Thank you. We're honored to have you anytime.
Okay, thank you. Okay, so, you know, there you have it. We've, you know, come to the end of this conference. This is a nodal point in our development. I want to say last night, okay, we actually raised from this the fairly modest size group here $31,000 in that session, which is going to give us the war chest that we need. Okay, okay, I'm gonna now you've given me the ammo, and now I'm gonna go hunting. To do the treks around, you know, I'm going to Los Angeles on Tuesday, and the next week I'm going to New York, and the next week I'm going to Atlanta, and the week after that I'll be going to somewhere else. But I'm going to find the funds to make this Mars Technology Institute a reality. Okay. And okay, and this thing is going to be epic. It's going to be something historic as Menlo Park, okay, or Bell Labs, okay, except this one, okay, is going to open the road to Mars and make possible planetary settlement actually anywhere where planetary settlement can be done, okay? And we're going to prove to the world, okay, really what space can do for humanity, that freedom can give us space and space can give us freedom. So thank you. And I hope to see you all next year. I'm not sure where we'll be. We could be here. It's possible we could be in Los Angeles again, or even in Seattle. Those are the three leading contenders. But wherever we are, wherever you go, there you are. Buckaroo Banzai.
All right, everyone. Thank you so much. This concludes the event. Have a safe trip home, and we'll see you next year.
On to Mars.